Hello there and welcome to Just About Earth, where curiosity gets comfortable, science takes its time, and the long story of our planet unfolds at a pace meant for winding down rather than rushing ahead. Tonight, we're setting aside the busy world of notifications, schedules, and glowing screens, and instead letting our thoughts drift backward, not by years or centuries, but by hundreds of millions of years, to a version of Earth that looked, felt, and behaved in ways that would barely resemble the place you know today. Imagine for a moment standing on a shoreline where no birds call overhead, no trees sway in the breeze, and no footprints remain in the sand because nothing has ever walked there. The waves still roll in though, the wind still moves across the surface of the sea, the sun still rises and sets, but the world itself feels quiet in a deeper way, as if it's waiting for something to begin. That waiting place in Earth's long history is where we're heading tonight, to a time when the planet's land was gathered into a single, enormous mass known as Penosia. It didn't last very long by geological standards, but while it existed, it helped shape the conditions that would eventually allow complex life to take its first meaningful steps forward. Before we settle into that ancient landscape, let me ask you something simple and gentle. Where are you listening from right now? Is it late evening, early morning, or somewhere in between? Are you curled up in bed, resting on a couch, or maybe letting this play softly in the background as the day fades out? It's a small question, but it's a reminder that while we're about to travel through deep time together, we're also very much here, in this moment, sharing this quiet space across whatever distance separates us. If this kind of slow, thoughtful wandering through Earth's story feels soothing to you, if it helps you relax or gives your mind a soft place to land, you might consider liking the video or subscribing. It helps this calm corner of science reach others who may also be looking for something gentle to listen to at the end of a long day. And now, with that said, let's begin easing our way into a world that existed long before the first leaf, the first feather, or the first pair of curious human eyes ever appeared. Pannotia is not a name you'll hear very often outside of geology classrooms or quiet conversations between scientists who spend their lives thinking about deep time. It doesn't have the same recognition as Pangaea, the more famous supercontinent that came much later. But Penosia holds a special place in Earth's history, because it formed at a moment when the planet was balancing on the edge of enormous change. To understand what Earth was like during this period, it helps to start with the simple idea that the ground beneath your feet is not as still as it feels. Continents are not permanent fixtures. They drift, collide, tear apart, and reassemble over spans of time so long that they make human history look like a brief blink. This movement happens because the planet's outer shell is broken into massive plates that float on slowly churning rock deep below. They move at about the speed your fingernails grow, which doesn't feel like much until you give them a few 100 million years to work. By the time Penosia came together, Earth had already been through several of these continental cycles. Landmasses had merged and split apart before, and they would do so again. But the world that formed around Penosia was shaped by a particularly dramatic backdrop, one that included some of the coldest global conditions the planet has ever known. Long before this supercontinent took shape, Earth went through a series of extreme ice ages known as the Snowball Earth events. During these times, glaciers likely reached from the poles all the way to the equator, wrapping the planet in ice so extensive that even tropical oceans may have frozen over at the surface. It's difficult to picture a world like that. One where sunlight reflects off ice across most of the globe, and where life, if it exists at all, must cling to narrow pockets of survivable conditions beneath the frozen surface of the sea. By the time Penosia began to form, Earth was starting to emerge from these deep freezes. The ice was retreating, the oceans were opening up again, and the atmosphere was changing. Volcanoes, which never truly stopped working, even during the coldest periods, had continued to pump carbon dioxide into the air. Over long stretches of time, this greenhouse gas built up enough to trap heat and slowly warm the planet. The result was a dramatic shift from global ice to a world that, in some places, may have become surprisingly warm. So when the continents finally gathered into Penosia, they did so on a planet that had just come through one of the most intense climate swings in its history. The land was raw in many places, shaped by glaciers that had scraped and ground down rock, leaving behind vast deposits of sediment. Rivers began to carve new paths across the surface, carrying minerals into the oceans. Shallow seas spread across the edges of the land, forming wide, calm environments that would later become important for the next phase of life on Earth. If you were somehow able to hover above this ancient world, you wouldn't see forests, grasslands, or cities. You would see a single, sprawling mass of land surrounded by a global ocean. The coastline would stretch on for enormous distances, winding around bays, inlets, and shallow continental shelves. Inland, the terrain would likely be dominated by rocky plains, low mountain ranges, and wide areas of bare ground. The sky above Pannotia would feel familiar in one sense, because it would still be blue, still filled with clouds, still lit by the same sun. But the air itself would not be quite the same. Oxygen levels were lower than they are today, though they were slowly rising. There was no protective ozone layer like the one we rely on now, which meant more ultraviolet radiation reached the surface. For complex life on land, this would have been a serious problem, one of several reasons why nearly all living things at the time stayed in the water. The oceans, however, were quietly becoming places of opportunity. Beneath the surface of those ancient seas, life was already well established, though not in forms you would easily recognise. For most of Earth's history up to this point, life had been small and simple, made up of single-celled organisms and colonies of bacteria. These tiny beings were incredibly important. They produced oxygen, shaped the chemistry of the oceans, and laid the groundwork for everything that would come later. But during the time surrounding Penosia, something new was beginning to appear. The first truly complex multicellular organisms were starting to take shape. Soft-bodied creatures, often flat and frond-like, drifted or rested on the seafloor. They didn't have eyes, bones, or shells. They likely absorbed nutrients directly from the water around them. Even so, they represented a major step forward in the story of life. The environments created by Penosia may have played a role in this development. When a supercontinent forms, it changes the way oceans circulate. Currents that once flowed freely around separate landmasses are redirected. This can affect how heat, oxygen, and nutrients move through the seas. Shallow coastal waters, especially, can become rich in minerals washed down from the land. These areas often support a greater variety of life, even in modern oceans. Picture long, wide, continental shelves bathed in sunlight. The water is not very deep, allowing energy from the sun to penetrate and support photosynthetic organisms. Nutrients carried by rivers feed growing microbial communities. Over time, these conditions create stable, productive environments where more complex forms of life can experiment, adapt, and slowly become more diverse. While all of this was happening in the water, the land itself remained mostly quiet in biological terms. There were no plants to hold the soil in place, no roots to break up the rock, no animals to burrow or crawl. Wind and water were the main sculptors of the surface. When it rained, the water would run freely across the ground, carving channels and carrying sediment into the sea. When the wind blew, it would move dust across wide, open plains. Volcanoes added another layer of activity. Pannotia did not form in a moment of geological peace. The same forces that pulled the continents together also created zones of intense pressure and heat. Mountain ranges rose where land masses collided. Deep cracks opened where the crust began to stretch and thin. In these regions, molten rock from below the surface could find its way upward, spilling out as lava or exploding into the air as ash. These eruptions did more than reshape the landscape. They released gases into the atmosphere, including carbon dioxide and sulfur compounds, which influenced the climate. They also brought new minerals to the surface, enriching the land and eventually the oceans. Over long periods of time, this steady input of material helped change the chemistry of the planet in ways that mattered for life. If you were standing somewhere near the centre of Penosia, far from the coast, you might find yourself in a vast, dry interior. Large supercontinents tend to create these kinds of environments because moist air from the oceans has a harder time reaching deep inland. The result is often a climate that is more extreme, with greater temperature differences between day and night and less regular rainfall. Even without plants or animals, these regions would still have their own quiet rhythms. The sun would rise and heat the rocky surface. The air would shimmer. At night, temperatures would drop, and the sky would fill with stars, just as it does now. The same constellations you see today would be there, though in slightly different positions, because the stars themselves are also moving slowly across the galaxy. One of the remarkable things about thinking this far back in time is realizing how much of Earth's basic structure was already in place. The planet had an atmosphere, oceans, continents, a magnetic field, and a steady source of energy from the sun. The same fundamental processes that shape the world today, erosion, plate tectonics, the water cycle, were all working then too. The difference lay in what those processes were acting on. Without forests, reefs, or cities, the planet's surface responded more directly to physical forces. Rivers ran faster and muddier. Coastlines shifted more freely. Mountains eroded without roots to hold them together. The land was, in a sense, more exposed, more honest about the power of wind, water, and stone. As Penosia existed, it didn't stay perfectly still. Even while it was technically a single supercontinent, the forces that would eventually tear it apart were already at work. Heat from deep within the earth caused parts of the crust to rise and thin. Cracks formed. Magma pushed upward. Over millions of years, these weak points would grow and the land would begin to split. This is one of the quiet truths of Earth's history. Nothing that forms on a planetary scale stays that way forever. Mountains rise and wear down. Oceans open and close. Continents come together and drift apart. Pannotia was no exception. Its time as a unified landmass was relatively short, especially compared to some other supercontinents. But its presence marked a transition between an older, simpler world and a future that would soon become much more crowded with life. As you picture this ancient Earth, it can be helpful to let go of the idea that it was empty or lifeless, just because it didn't look like the world you know. The oceans were full of microscopic activity. Chemical reactions were constantly reshaping the environment. The planet itself was alive with motion, even if that motion unfolded at a pace far slower than any human lifetime. There's something calming about that thought. The idea that beneath all the noise and urgency of the modern world, Earth still moves to these deep, steady rhythms. Plates still drift. Mountains still rise and fall. The cycle that brought Penosia together and then pulled it apart is the same one that shapes the continents you live on now. For now, though, it's enough to sit with the image of a quiet planet, just emerging from deep cold, its continents gathered into one, its oceans beginning to stir with new possibilities. Earth, at this moment in its history, is not yet the busy, colourful place it will become, but it is preparing, in its own slow and steady way, for a transformation that will change the surface of the world forever. Let's ease forward from that wide, quiet view of an ancient Earth and begin to focus on the land itself, not just as a backdrop, but as a moving, shifting presence with a story of its own. Imagine the surface of the planet as a slow, patient puzzle, where enormous pieces of crust drift across a sea of heat and pressure, sometimes gliding past each other, sometimes locking together, sometimes pulling apart with a kind of deep, rumbling determination. Over spans of time so long they almost stop feeling like time at all, those pieces come together to form something larger, something that briefly feels whole before the motion starts all over again. This is where Penosia enters the picture, not as a sudden event or a dramatic moment, but as the quiet result of countless small movements adding up to something enormous. The name itself, Penosia, comes from Greek roots meaning all the south, reflecting the idea that most of the land involved in this supercontinent was clustered in the southern hemisphere. But names are something we add much later, long after the rocks have finished moving. At the time, there was no sense of a single unified landmass. There was just the slow, steady convergence of continents, inch by inch, over millions of years. To get a feel for how this happened, it helps to picture the Earth's outer shell as a mosaic of massive plates. These plates float on a layer of hotter, softer rock below, which moves in slow, rolling currents driven by heat from deep inside the planet. Where these plates meet, things happen. Sometimes one plate slides under another, sinking back into the Earth's interior. Sometimes they grind past each other, building tension. Sometimes they crash together, forcing the crust upward into mountain ranges. In the long lead-up to Pannotia's formation, several large land masses were on a gradual collision course. Among them were ancient versions of what would one day become parts of Africa, South America, Australia, Antarctica, and smaller continental fragments that no longer exist as independent pieces today. They were not moving quickly by any human standard, but over tens of millions of years, even the slowest drift can carry a continent halfway across the planet. As these land masses approached each other, the spaces between them, ancient oceans that had existed for hundreds of millions of years, began to shrink. Oceanic crust, which is thinner and denser than continental crust, was pushed down beneath the edges of the continents in a process known as subduction. As it sank, it melted, contributing to volcanic activity along the continental margins. Chains of volcanoes likely line the coasts, adding new rock to the edges of the land and slowly stitching the continents together. This kind of collision leaves marks that geologists can still find today. Deep in mountain ranges across the modern world, there are rocks that once formed on the floor of ancient oceans. There are layers of volcanic material that speak of long-gone arcs of fire. There are bands of compressed and twisted stone that tell a story of immense pressure, of land being forced against land with nowhere else to go but up. By studying these clues, scientists can piece together a rough picture of how Penosia came to be, even though the supercontinent itself no longer exists as a single intact body. The continents that once made it up have since drifted apart, travelled across the globe, and rearranged themselves into the familiar shapes we see on maps today. What makes Penosia especially interesting is how brief its time as a unified supercontinent seems to have been. In geological terms, brief still means tens of millions of years, but compared to other supercontinents, it appears to have formed and then begun to break apart relatively quickly. This gives it a slightly elusive quality, like a guest who arrives, stays just long enough to make an impression, and then quietly slips out before anyone fully settles into their presence. Reconstructing the shape of Penosia is a bit like trying to assemble a puzzle, when most of the pieces have been reshaped, broken, or reused in other puzzles over time. Rocks that were once neighbours are now separated by entire oceans. Layers that formed side by side have been buried, heated, and transformed into new kinds of stone. Still, with enough careful work, patterns begin to emerge. One of the key tools scientists use is the magnetic record locked inside rocks. When volcanic rocks cool, tiny magnetic minerals inside them align with Earth's magnetic field at that moment. Because the magnetic field has changed direction many times over the planet's history, these alignments act like timestamps and compasses combined. By measuring them, researchers can tell not only how old a rock is, but also where on the planet it formed, in terms of latitude. By comparing these magnetic signatures across continents, it becomes possible to see which landmasses were once connected, and roughly how they were arranged. This method, along with the study of matching rock types and fossil distributions, allows geologists to sketch out a map of Penosia, even though the original has long since been torn apart. The picture that emerges is of a supercontinent that looked somewhat different from the more famous Pangaea. Rather than a single, compact mass, Penosia may have had a more irregular shape, with large embayments of ocean cutting into it. Some researchers describe it as resembling a loose cluster of land centred around the South Pole, with long coastlines and extensive shallow seas along its edges. Those coastlines are important, because they would have been among the most active and interesting places on the planet at the time. Where land meets sea, energy flows. Waves break down rock, rivers deliver sediment, nutrients mix into the water. Even in a world without fish, coral or plants, these boundary zones would have been hotspots for chemical and biological activity. Farther inland, the story would have been different. The interior of a supercontinent can become dry and extreme because moisture from the oceans has a hard time reaching the centre. Air masses drop their rain near the coasts and mountain ranges, leaving the heart of the land relatively arid. During Penotia's time, this may have created wide, barren regions dominated by rock, dust, and occasional streams that flowed only after rare precipitation events. Temperature differences between day and night could have been more pronounced in these areas. Without vegetation to moderate the climate, the surface would heat up quickly under the sun and cool rapidly after dark. The result would be a land of strong contrasts, not in the sense of forests and deserts, but in the simple, physical feel of warmth and cold, light and shadow. Even though life on land had not yet taken hold, these physical conditions still mattered for what was happening in the oceans. The weathering of rock on the surface released minerals into rivers, which carried them to the sea. These minerals, including elements like phosphorus and iron, are essential for life. Their availability can influence how much biological activity an ocean can support. As Penosia formed, the changing shape of the land altered the flow of ocean currents. When continents move, they can block or redirect the paths that water takes around the globe. This affects how heat is distributed, which in turn influences climate. It also affects how nutrients are mixed through the oceans, shaping the environments where early complex life was beginning to develop. There is a quiet but powerful connection here between moving rock and living cells. The arrangement of continents can set the stage for biological change, even if the continents themselves are completely unaware of the role they are playing. One way to think about Penosia is not just as a piece of Earth's geological history, but as part of a long chain of cause and effect. The collisions that formed it created mountain ranges that eroded into sediments. Those sediments fed shallow seas. Those seas provided stable environments for early multicellular organisms. Those organisms, over time, became the ancestors of the more complex life that would later explode into diversity during the Cambrian period. None of this happened quickly. There was no sudden moment where the world changed overnight. Instead, it was a slow layering of conditions, one on top of another, each making the next step a little more possible. From a human perspective, it can be hard to connect with something that unfolds over hundreds of millions of years. Our own lives feel long if they span a few decades. Even recorded history stretching back a few thousand years is a tiny sliver compared to the age of the planet. Pannotia existed more than 500 million years ago. The mountains that formed when its continents collided have been worn down, buried, and in some cases lifted up again in entirely new shapes. And yet, pieces of that world are still with us. The rocks beneath your feet may contain minerals that were once part of a Pannonian mountain range. The sand on a beach might include grains that began their journey as volcanic ash along an ancient coastline. The story of that supercontinent is not locked away in the past. It's built into the physical world around you, even if it's hidden beneath layers of time and change. There's something quietly grounding about that idea. The notion that the Earth you know today is not a finished product, but a moment in a much longer process. Penosia was once a now in the planet's life, just as your present moment is a now in yours. Both are fleeting in their own way, even if one lasts for millions of years and the other lasts for a single breath. As Pannotia reached its fullest extent, the forces that created it did not stop. Heat continued to rise from the planet's interior. The plates continued to move. Stresses built up in the crust, especially in areas where the land had been stretched thin. Over time, cracks began to form. Magma pushed up through these weak points, creating new volcanic regions. The crust started to sag and split in places, marking the earliest signs of the supercontinent's eventual breakup. This is another feature that makes Penosia feel slightly different from some of its predecessors and successors. It seems to have formed and begun to fragment in relatively quick succession. In geological terms, it didn't settle into a long, stable configuration. It was more like a transitional state, a bridge between older continental arrangements and the world that would soon give rise to the Cambrian explosion of life. While the land was shifting and cracking, the oceans responded. New seaways opened. Shallow basins formed where the crust dipped. Water flowed into these low areas, creating wide, warm, sunlit environments. These kinds of settings are especially important for biological innovation. They offer a mix of stability and change, shallow depths where light can penetrate, and constant input of nutrients from nearby land. It's not a coincidence that the rise of more complex life seems to follow closely on the heels of Penosia's breakup. The rearrangement of continents and oceans created a patchwork of new habitats, each with slightly different conditions. In this diversity of environments, life had more opportunities to adapt, specialize, and diversify. So when we talk about meeting Penosia, it's not just about introducing a name or a shape on a map. It's about recognizing a moment in Earth's history when geology and biology were deeply intertwined. The movement of rock set the stage for the movement of life, even if that life was still mostly soft, simple, and hidden beneath the waves. There's a quiet elegance in that connection. The idea that something as solid and seemingly unchanging as a continent can influence something as delicate and dynamic as a living cell. The idea that the slow grind of tectonic plates can echo forward in time, shaping the conditions that eventually allow eyes to see, lungs to breathe, and minds to wonder about where it all began. As you let this image settle, a single irregular landmass drifting slowly across a restless planet, surrounded by ancient seas and under an unfamiliar sky, it becomes easier to see Penosia not as a distant abstract concept, but as a real place that once existed, with its own climates, coastlines, and rhythms. Before the world gathered itself into the shape we've just been getting to know, before the continents drifted close enough to brush their edges and begin the long, grinding process of becoming one, Earth was already deep into a chapter of its history that feels both distant and strangely familiar. This was the Neoproterozoic, a stretch of time that unfolded roughly between 1 billion and 540 million years ago, and it was anything but quiet, even if, from far away, it might seem like a calm, empty prelude to everything that came after. If you could step back far enough to watch the planet during this era, you would see a world in motion, not in the quick, visible ways we're used to, but in slow, persistent shifts that reshaped the surface and the environment over tens of millions of years. The continents were not where you would find them on a modern map. The oceans flowed along unfamiliar paths. The air itself carried a different mix of gases, and life, though still mostly small and hidden, was steadily laying the groundwork for a transformation that would soon ripple across the entire planet. One of the first things that would stand out to you is the sense of scale. The Neoproterozoic lasted for hundreds of millions of years, long enough for entire mountain ranges to rise and be worn down again, long enough for oceans to open and close, long enough for the chemistry of the atmosphere to shift in ways that would change what kinds of life could survive. It's a span of time so broad that even Penosia, with all its drifting land and shifting seas, fits into it as just one phase in a much larger story. At the beginning of this era, Earth's surface was still carrying the marks of earlier supercontinents that had formed and broken apart. Ancient mountain belts, The roots of long-eroded ranges were scattered across the land. The crust in many places was thick and stable, having survived countless cycles of collision and separation. But stability, on a planet like Earth, is always temporary. Deep below the surface, heat from the planet's interior continued to drive slow, rolling currents in the mantle. These currents pushed against the plates of the crust, urging them apart in some places and forcing them together in others. Where plates pulled away from each other, new oceanic crust formed as molten rock rose and cooled. Where they collided, land crumpled and thickened, building new highlands and mountain chains. All of this movement shaped the layout of the oceans. During the Neoproterozoic, vast stretches of water separated the major landmasses. These ancient seas were not just empty spaces between continents. They were active, dynamic systems that moved heat around the planet, mixed nutrients, and influenced climate patterns in ways that were sometimes gentle and sometimes extreme. And extreme is a word that comes up often when talking about this period, especially when it comes to climate. The Neoproterozoic is famous for hosting some of the most intense ice ages Earth has ever experienced. These are often grouped under the term snowball Earth, a phrase that captures the idea of a planet wrapped almost entirely in ice. While scientists still debate the exact extent of these glaciations, there is strong evidence that ice sheets reached very low latitudes, possibly even covering regions near the equator. Imagine a world where glaciers stretch from the poles toward the tropics, where much of the ocean surface is sealed beneath thick layers of ice, and where sunlight reflects back into space instead of warming the planet. In such a scenario, the usual patterns of climate and weather break down. The difference between winter and summer becomes less important than the difference between ice-covered and ice-free zones. Life, in this setting, faces enormous challenges. Photosynthetic organisms, which rely on sunlight, must find ways to survive beneath ice or in small, open patches of water where light can still penetrate. Other forms of life may retreat to deeper waters where the temperature remains more stable. Hydrothermal vents on the seafloor, powered by Earth's internal heat, could provide pockets of warmth and chemical energy, acting as refuges during the coldest times. These global freezes did not last forever. Over millions of years, volcanic activity continued to release carbon dioxide into the atmosphere. Normally, this gas is balanced by processes that remove it, such as weathering of rocks and the formation of carbonate minerals. But when much of the planet is locked in ice, those balancing processes slow down. Carbon dioxide builds up, strengthening the greenhouse effect. Eventually, this buildup becomes strong enough to tip the planet out of its frozen state. Temperatures rise, ice begins to melt. The transition from a snowball Earth to a warmer world may have been rapid and dramatic, with massive floods of melt water pouring into the oceans and reshaping coastlines across the globe. It's in the wake of these great climate swings that the scene for Penosia begins to take shape. The world that emerges from the ice is not just warmer, but chemically and biologically different. The oceans receive an influx of minerals from newly exposed rock. The atmosphere carries higher levels of oxygen than it did in earlier eras, though still not as much as today. These changes create new opportunities for life to expand and experiment. But before we follow that thread, it's worth spending a little time with the atmosphere itself, because during the Neoproterozoic, the air above the planet was undergoing its own slow evolution. For much of Earth's early history, oxygen was a rare and reactive gas, produced mainly by photosynthetic microbes and quickly consumed by reactions with rocks and dissolved minerals. Over time, as those sinks became saturated, oxygen began to accumulate in the atmosphere. This process, often called the Great Oxidation, started long before the Neoproterozoic, but its effects continued to unfold well into this era. By the time we reach the later part of the Neoproterozoic, oxygen levels were high enough to support more complex forms of life. This doesn't mean the air was comfortable by modern standards. Breathing it would likely still feel thin and unfamiliar, but it marked a crucial threshold. Oxygen allows cells to extract much more energy from food than they can through simpler chemical pathways. That extra energy can be used to build larger, more complex bodies, to support specialized tissues, and to power movement. So while the surface of the planet was being reshaped by ice, water, and moving rock, the invisible layer of air above it was quietly setting the stage for a biological shift. The oceans, too, were changing in ways that would have long-lasting effects. The chemistry of seawater is influenced by what flows into it from the land, what falls into it from the atmosphere, and what happens within it as life grows and dies. During the Neoproterozoic, repeated cycles of glaciation and melting likely caused large swings in ocean chemistry. When glaciers grind across rock, they produce fine sediments and release minerals. When those glaciers melt, the material is carried into rivers and then into the sea. This can increase the availability of nutrients that life depends on, such as phosphorus and iron. At the same time, melting ice adds fresh water to the oceans, which can affect how layers of water mix and how oxygen is distributed with depth. In some scenarios, these changes may have led to periods where parts of the ocean became low in oxygen, especially in deeper waters. This kind of environment can be challenging for many forms of life, but it can also drive adaptation, pushing organisms to find new ways to survive, or new places to live. All of this means that the Neoproterozoic was not a simple, steady march toward complexity. It was a time of stress and opportunity, of harsh conditions followed by relative calm, of environmental pressures that tested the limits of what life could endure. And life did endure. For most of this era, the dominant forms of life were still microscopic. Bacteria and other single-celled organisms filled the oceans, forming mats on the seafloor, floating in the water, and coating rocks in slimy layers. These communities were not passive. They altered their surroundings by producing oxygen, trapping sediments, and participating in chemical cycles that affected everything from the colour of the water to the composition of the air. In the later part of the Neoproterozoic, something new begins to appear in the fossil record. Soft-bodied multicellular organisms, often grouped under the name Ediacaran biota, start to show up as impressions in ancient sediments. These creatures are strange by modern standards. Many look like flat discs, fronds, or quilted patterns pressed into stone. It's not always clear how they lived, what they ate, or how they moved. Some may have absorbed nutrients directly from the water. Others might have grazed on microbial mats. A few could have been early attempts at more active lifestyles, though nothing from this group looks quite like the animals that would dominate the seas later on. What they represent more than anything is a shift in possibility. The environment had reached a point where larger, more complex organisms could exist and persist. The energy available in the system, the chemistry of the oceans, and the composition of the atmosphere all combined to make room for these experiments in form and function. As these early multicellular life forms spread across shallow sea floors, they interacted with their environment in new ways. They could disturb sediments, change how water flowed near the bottom, and create small-scale structures that influenced where other organisms could live. In doing so, they began to modify the planet in ways that went beyond simple chemical reactions. This is another quiet theme of the Neoproterozoic, the idea that life and Earth were shaping each other, not in dramatic visible ways, but through countless small interactions that added up over time. While this biological story was unfolding in the water, the land remained largely bare. There were no plants to anchor the soil, no insects to crawl over the surface, no animals to dig burrows. The only signs of a life on land would have been microbial films in damp areas, perhaps thin layers of bacteria clinging to rock near the edges of water. Because of this, erosion worked differently than it does today. Rain falling on rock could wash material away quickly, creating muddy rivers that carried large amounts of sediment to the sea. Without roots to hold the ground in place, landscapes could change more rapidly in response to storms or shifts in climate. The shapes of coastlines during this time were influenced not just by the slow rise and fall of sea level, but by the steady delivery of sediment from the land. Deltas could grow outward into the ocean. Shallow bays could fill in. New stretches of flat, muddy seafloor could form, providing fresh habitat for the growing community of early multicellular organisms. All of this was happening while the continents themselves were on the move, slowly approaching the configuration that would become Penosia. The Neoproterozoic, in this sense, is a long lead-in, a setting phase where the pieces are being arranged, the conditions tested, and the players introduced. There's a certain calm that comes from viewing this period from a distance, even though it includes some of the most extreme climate events in Earth's history. The calm is not in the events themselves, but in the pace at which they unfold. Ice ages last millions of years. Continental collisions take tens of millions more. Changes in atmospheric composition happen over spans of time that stretch far beyond any individual lifespan. It's a reminder that the planet operates on a different clock than we do. From the perspective of the Earth, a global freeze is not a sudden disaster. It's a phase. From the perspective of life, it's a challenge to be met with patience, adaptation, and persistence. And from our perspective, looking back across deep time, it's part of a pattern of change that has repeated in different forms again and again. As the Neoproterozoic moves toward its later stages, the extremes begin to soften. The last of the great glaciations fade, the climate becomes more stable, at least for a while. Sea levels rise as ice melts, flooding large areas of the continents and creating broad, shallow marine environments. These environments are especially important because they tend to be biologically productive. Sunlight reaches the bottom, nutrients from the land mix easily into the water. Temperatures are relatively moderate. It's in settings like these that life can diversify and spread. This is the calm hinted at in the idea of Earth before the calm. It's not a perfect stillness, and it's certainly not permanent, but it's a window of relative stability after long periods of upheaval. A moment when the planet's systems, climate, oceans, and atmosphere align in a way that supports growth and experimentation. At the same time, the tectonic forces that will soon gather the continents into Pannotia continue their slow work. Landmasses draw closer, ocean basins narrow, mountain belts rise where collisions occur, volcanic arcs trace the edges of shrinking seas. The world is being prepared, both physically and biologically, for what comes next. There's a gentle continuity in this process. The Neoproterozoic doesn't end with a sharp boundary in the way we might expect from a story with clear chapters. Instead, it blends into the conditions that allow Penosia to form and, soon after, into the events that will lead to the Cambrian explosion, when life's diversity will expand in a way that leaves a much clearer and richer fossil record. Though, it's enough to hold on to the image of a planet emerging from ice, its air slowly filling with oxygen, its oceans stirring with new kinds of life, and its continents drifting toward a brief moment of unity. It's a world in transition, balanced between extremes and opportunities, carrying the memory of deep cold and the promise of biological change. If you were to press your ear gently against the ground and listen for the sound of Earth moving, you wouldn't hear anything at all. No creaks, no rumbles, no steady rhythm like a heartbeat. And yet, beneath every landscape, beneath every ocean, beneath every mountain and plain, the planet is always in motion. It's a kind of movement that unfolds so slowly that it feels invisible, but over enough time, it can gather whole continents together and then pull them apart again, like pieces of a puzzle rearranged by an unhurried hand. This slow choreography is what eventually brought the world's land into the shape we call Penosia, and it begins far below the surface, in a place we can't see and can only imagine through the clues it leaves behind. Deep inside the Earth, closer to the core than to the sky, heat left over from the planet's formation, along with heat produced by the slow decay of radioactive elements, keeps the mantle in a state that's neither fully solid nor fully liquid. It behaves more like a very thick, very slow-moving fluid. Over millions of years, this material rises where it's warm and sinks where it's cooler, setting up vast convection currents that move through the planet's interior. The outer shell of the Earth, known as the lithosphere, rests on top of this moving layer. It's broken into enormous plates, some carrying continents, others carrying ocean floors. These plates are the pieces of the puzzle, and the mantle currents beneath them are the quiet, persistent force that nudges them along. In some places, the plates are being pushed apart. This often happens along long underwater mountain chains called mid-ocean ridges. Here, molten rock wells up from below, cools as it meets the ocean water, and solidifies into new crust. As more material rises and hardens, it pushes the existing plates away from the ridge, widening the ocean basin a little more each year. In other places, plates are moving toward each other. When a denser oceanic plate meets a lighter continental one, the oceanic plate usually slides underneath in a process called subduction. It sinks back into the mantle, melts, and can eventually contribute to volcanic activity on the surface. When two continental plates collide, neither one easily goes under. Instead, they crumple and thicken, pushing up mountain ranges that can stretch for thousands of kilometers. This constant creation and destruction of crust is what keeps the surface of the planet dynamic. Oceans open and close. Mountains rise and erode. Continents wander across the globe. During the long lead up to Penosia, several major landmasses were on a slow journey toward each other. These included ancient versions of Gondwana's building blocks, pieces that would later become Africa, South America, Antarctica, Australia, and parts of what we now call Asia and Europe. At the time, they were separated by wide oceans with names like the Mozambique Ocean and the Adamaster Ocean, bodies of water that existed for hundreds of millions of years before vanishing completely. As the plates moved, these oceans began to shrink. Subduction zones formed along the edges of the continents, where the ocean floor was pulled down into the mantle. Over time, the distance between the land masses narrowed. Island arcs, chains of volcanoes that form above subduction zones, rose from the sea, sometimes becoming stepping stones that hinted at the coming collision. The approach of two continents is not a quiet affair, even if it happens slowly. The leading edges of the land are often marked by intense geological activity. Earthquakes shake the crust as stresses build and release. Volcanoes add new layers of rock to the surface. Sediments pile up in deep basins offshore, formed from material eroded off the rising highlands. As the gap between the continents closes, the ocean between them becomes shallower. Eventually, the last sliver of oceanic crust disappears beneath one of the plates, and the two continents meet. There is no single moment you could point to and say, this is when they touched. Instead, it's a drawn-out process, a long phase of deformation where the crust thickens, folds, and reshapes itself under immense pressure. This is how some of the world's great mountain belts are born. The Himalayas, for example, are still rising today because India is continuing to push into Asia. During the time leading up to Pannotia, similar processes were happening across different parts of the planet, creating ancient ranges that have since been eroded down to their roots. The collision zones of that era left behind rocks that tell stories of extreme conditions. Some were buried deep within the crust, subjected to enormous heat and pressure, and transformed into metamorphic rocks with distinctive textures and mineral compositions. Others were squeezed into tight folds, like layers of fabric pushed together from both ends. By finding and studying these rocks on different continents, geologists can match up pieces of the puzzle. If two distant regions contain the same types of rocks, of the same age, formed under the same conditions, it's a strong hint that they were once part of the same mountain belt, and therefore once connected. But the story of how the continents drifted into one is not just about collisions. It's also about the quieter spaces in between, the long stretches of ocean that slowly changed character as the land masses moved. Ocean currents, for instance, would have been influenced by the shifting geography. When continents are spread out, water can circulate more freely around the globe. As they come together, those pathways become more constrained. currents are redirected, which can change how heat is distributed between the equator and the poles. These changes in circulation can affect climate. If warm water is prevented from flowing into certain regions, those areas can cool. If cold water is blocked, other regions can warm. Over long periods, this can contribute to broader climate trends, adding another layer to the already complex story of the Neoproterozoic's extreme conditions. The continents themselves also influence the atmosphere. Large land masses can disrupt wind patterns, creating zones of rising and sinking air. This can affect where clouds form and where rain falls. As Penosia took shape, these atmospheric patterns would have shifted, potentially creating wide interior regions that were drier and more extreme than the coastal areas. One way to picture this is to imagine a vast, unbroken stretch of land, far from any ocean. Moist air from the sea loses much of its water as it moves inland, dropping rain along the way. By the time it reaches the centre, there is little left to fall. The result is a landscape that receives very little precipitation, even if the world around it is relatively wet. This kind of interior dryness has been a feature of other supercontinents, and it likely played a role during Penosia's time as well. The land in these regions would have been shaped mostly by wind and occasional flash floods, rather than steady rivers or lush vegetation. While all of this was happening at the surface, the deeper processes that drove plate motion continued without pause. The mantle currents that push the plates along are influenced by the distribution of heat inside the Earth. Regions where the mantle is hotter tend to rise, creating broad uplifts at the surface. Where it's cooler, it sinks, pulling plates downward. Over time, this can create patterns of stress in the crust. Areas under tension may begin to thin and crack. Magma can rise into these fractures, forming new volcanic regions. If the process continues, a continent can begin to split apart, creating a rift that may eventually widen into a new ocean basin. This is the same kind of process that is happening today in places like the East African Rift, where Africa is slowly being pulled into two pieces. During the era of Penosia's formation, similar rifts likely existed elsewhere on the planet, even as other regions were being pushed together. This creates a sense of balance in the system. While one part of the world is coming together, another part is being pulled apart. The total amount of crust remains roughly the same, but its arrangement is constantly changing. In the long approach to Penosia, the balance tipped toward convergence. More ocean basins were closing than opening, and the major landmasses were gradually clustering together. This did not happen in a neat, symmetrical way. Some regions collided earlier than others. Some connections were temporary, later breaking apart and reforming in slightly different configurations. This is one reason why reconstructing the exact shape of Penosia is such a challenge. The process was messy, overlapping and spread out over time. There may not have been a single moment when all the continents were perfectly joined in a stable configuration. Instead, there was a window during which most of them were connected in some way, even if the connections were still shifting. The rocks preserve hints of this complexity. In some places, you find evidence of multiple phases of deformation, suggesting that an area was involved in more than one collision event. In others, you find volcanic layers that point to periods of extension, when the crust was being pulled apart rather than pushed together. Another piece of the puzzle comes from the distribution of ancient sediments. Thick layers of sedimentary rock often form in basins created by tectonic processes. By dating these layers and analysing their composition, scientists can infer when and where the crust was sinking or rising. For example, a deep basin filled with marine sediments might indicate a region that was once underwater, perhaps between two approaching continents. Later, if that same area contains signs of uplift and erosion, it suggests that the continents eventually collided and pushed the basin upward. These kinds of transitions, recorded in stone, help build a timeline of how the land moved and changed. As the continents drew closer, the nature of the coastlines would have changed as well. Wide, open shelves might have narrowed. Shallow seas could have been squeezed out of existence in some areas, while new ones formed elsewhere. The shifting shape of the land would have continually altered the environments available to life in the oceans. Some shallow habitats might have disappeared as the land rose or the sea retreated. Others might have expanded as new basins formed. This constant turnover could have encouraged early life to adapt, migrate, or find new niches. There's an interplay here between stability and change. Life often benefits from stable conditions, where environments remain relatively predictable over long periods. But it also evolves in response to change, when new challenges and opportunities arise. The slow drift of continents provides both long stretches of gradual transformation, punctuated by more abrupt shifts when collisions or rifting events occur. It's also worth remembering that gravity plays a role in this story. When continents come together, the thickened crust can sit higher above sea level, forming broad uplands. When they pull apart, the thinning crust can sink, allowing the sea to flood in. These vertical movements, known as isostatic adjustments, add another layer of complexity to how the surface of the planet changes. A region that was once a high plateau can become a shallow sea, and vice versa, simply because the weight of the crust above or below has changed. As Penosia approached its moment of near unity, these processes combined to create a world of varied landscapes, even within a single supercontinent. Mountain ranges traced ancient collision zones. Low-lying basins marked areas of extension or heavy sedimentation. Long coastlines wrapped around the edges of the land, where the influence of the global ocean was strongest. From a distance, the planet might have looked calm, a blue sphere with a single large landmass. But up close, it would have been a place of constant, if slow, activity. There's a kind of patience built into this system. The Earth does not rush. It does not aim for a final shape. It moves, responds, and reshapes itself in an ongoing conversation between heat, gravity, rock, and water. For those of us used to thinking in terms of days and years, it can be hard to connect with that scale. But there's something steadying about it. The idea that no matter what happens on the surface, the deeper rhythms of the planet continue, unbothered by the passage of individual lives or even entire species. As the continents finally drew close enough to be considered parts of a single whole, the world entered a new phase. The oceans were reshaped, the atmosphere responded, the environments available to life shifted again. But even at this point of near unity, the seeds of separation were already being sown. The same forces that brought the land together were creating stresses that would, given enough time, pull it apart again. This ongoing cycle, gathering and dispersing, forming and breaking, is one of the defining patterns of Earth's history. Penosia is one expression of that pattern, a moment when the pieces of the world happen to align in a particular way. Step back just a little from the slow motion of drifting continents and imagine the world as a whole, not as lines on a map or pieces of crust sliding past each other, but as a single, living planet suspended in space. During the time when Penosia existed, Earth would have looked both familiar and deeply strange. A place of blue oceans and white clouds, but also a place where ice, bare stone, and wide, quiet seas dominated the surface in ways that would feel almost empty to modern eyes. If you could drift above the planet far enough away to see its curve, the first thing you might notice is how much of it was water. Even then, oceans covered most of the surface, wrapping around the clustered land in a continuous, restless band. But the distribution of that water, and what it was doing, was shaped by the way the continents had come together. Large stretches of coastline traced the edges of Penosia. These were not the narrow, sharply defined shores you might picture today, backed by forests or cliffs. Instead, many of them were broad, gently sloping shelves, where the land met the sea in shallow, sunlit water that could extend for hundreds of kilometers before dropping away into the deeper ocean. These shallow seas were among the most important features of the planet at the time. They were places where light could reach the seafloor, where water moved slowly enough to let sediments settle, and where nutrients carried from the land could mix easily into the marine environment. In a world where life was still mostly confined to the water, these zones offered some of the best opportunities for growth, experimentation, and survival. But before we linger too long in those gentle coastal waters, it's worth turning our attention to the other dominant presence of this unfamiliar planet: the ice. The memory of global glaciation was still fresh in Earth's systems. Even as the planet warmed and ice retreated, cold conditions remained a powerful influence, especially at higher latitudes and in elevated regions. Large ice sheets likely covered significant portions of the land, particularly toward the poles and in mountainous areas created by recent continental collisions. These glaciers were not static. They moved slowly and heavily, grinding across the surface of the rock beneath them. As they advanced, they scraped away soil and stone, carving valleys and flattening high points. As they melted back, they left behind thick layers of debris, a mix of fine sediments and large angular rocks scattered across the landscape. This process had a quiet but far-reaching effect on the rest of the planet. The material left behind by melting glaciers didn't stay in place. Rain and meltwater picked it up and carried it into rivers, which in turn delivered it to the oceans. Over long periods of time, this steady flow of sediment reshaped coastlines, filled in shallow basins and altered the chemistry of the seas. So even in places far from the ice itself, the presence of glaciers was felt. If you were standing somewhere on the surface of Penosia, the land around you would likely look stark. There were no trees, no grasses, no fields of flowers or shrubs. The ground would be a mix of exposed bedrock, loose gravel, and patches of fine sediment. In some areas, the rock might be smoothed and rounded by the passage of ice. In others, it might be fractured and jagged, shaped by heat, pressure, and the slow pull of gravity. The sky above would feel wide and open. Without tall plants or structures, there would be nothing to block your view of the horizon. Clouds would still form and move with the wind, driven by the same basic processes of evaporation and condensation that operate today. Rain would fall, snow would settle in colder regions. The water cycle, one of Earth's oldest and most reliable systems, would continue its steady work of moving moisture from sea to sky to land and back again. But the way that water interacted with the surface would be different. Without vegetation to absorb it or roots to hold the soil together, rainfall could quickly turn into runoff. Streams might form suddenly after storms, carrying large amounts of sediment before drying up again. Rivers could change course more easily, carving new channels across the open landscape. These rivers were the planet's arteries, linking the land and the sea. They carried not just water, but minerals dissolved from rock, tiny particles of soil, and chemical compounds that would influence the life waiting in the oceans. Over time, they built deltas at their mouths, spreading out fans of sediment that created new stretches of shallow water. If you follow one of these rivers from its source to the coast, you can trace a kind of journey that mirrors the larger story of the planet. It begins high in the interior, perhaps in a region of low mountains or rolling uplands formed by ancient collisions. It winds through wide, open plains, gathering water from smaller streams along the way. Eventually it slows as it approaches the sea, dropping its load of sediment and spreading out into a network of channels that feed into the shallow coastal waters. These deltas and shelves would have been among the most active and productive environments on Earth at the time, not in terms of visible life, but in terms of chemical and biological potential. Sunlight reached the bottom, nutrients were abundant, water was constantly being mixed by waves and tides. It's in places like this that early multicellular organisms likely found a foothold. Soft-bodied life forms could spread across the seafloor, forming communities that interacted with the sediment and the water above. Microbial mats, already well established, would have provided both food and structure, trapping particles and stabilizing the surface of the sea bottom. While the shallow seas were busy in their own quiet way, the deeper oceans beyond them followed a different rhythm. Far from the influence of the land, the water would have been colder and darker. Sunlight faded quickly with depth, and the chemistry of the water changed. In some regions, the deeper layers of the ocean may have been low in oxygen. This kind of stratification, where lighter, oxygen-rich water sits on top of heavier, oxygen-poor water, can persist for long periods if mixing is limited. It creates distinct zones, each with its own conditions and challenges for life. The movement of ocean currents plays a key role in how these layers form and break down. During Penosia's time, the arrangement of the continents would have influenced how water flowed around the globe. Large land masses can act like walls, redirecting currents and creating large circular patterns of movement called gyres. These currents move heat as well as water. Warm water from lower latitudes can be carried toward the poles, moderating temperatures. Cold water can flow toward the equator, cooling the tropics. The exact patterns depend on the shape of the continents and the depth of the ocean basins. With much of the land clustered together, some of the global circulation pathways that exist today may have been restricted. This could have contributed to stronger temperature contrast between different regions of the ocean and to the persistence of ice in some areas even as the planet as a whole warmed. Above all of this, the atmosphere wrapped around the planet in a thin dynamic layer. The composition of the air during this time was different enough from today's to matter, but similar enough to feel recognizable in broad terms. Nitrogen still made up the majority of the atmosphere. Oxygen was present, though at lower levels. Carbon dioxide, a key driver of climate, varied over time depending on volcanic activity and how much was being removed by chemical reactions with rocks and oceans. The lack of land plants meant that one of the major modern influences on atmospheric composition was absent. Today, forests and grasslands play a huge role in cycling carbon and oxygen. During Penosia's time, that role fell almost entirely to marine organisms and to chemical processes involving rocks and water. Weather patterns would have been shaped by the size and shape of the supercontinent. Large interior regions could experience more extreme conditions, with hotter days and colder nights. Coastal areas, influenced by the ocean, would have had more moderate temperatures. Storms would still form where warm, moist air rose and cooled, releasing rain. Over the shallow seas, these storms could stir up the water, mixing nutrients from the bottom into the upper layers where light was available. This kind of mixing can boost biological activity, even in a world where life is still mostly simple and small. The interplay between ice, rock, and shallow seas created a planet of contrasts. Cold and warmth existed side by side. Stability and change were woven together. In one region, a glacier might be slowly grinding down a mountain. In another, a warm sunlit shelf might be hosting a quiet expansion of early multicellular life. There's something almost meditative about holding all of this in mind at once. The idea of a planet that is both harsh and gentle, both empty and full of potential. If you were able to walk along one of Penosia's coastlines, you might hear the familiar sound of waves breaking, the steady rhythm of water meeting land. You might feel the wind coming off the sea carrying salt and moisture, but you would not hear birds or insects. There would be no rustling of leaves, no calls echoing from the sky. The soundscape would be simpler, dominated by the elements themselves. The smell of the air might be different too, influenced more by the ocean and by volcanic gases in some regions than by vegetation. In areas of active tectonics, you might see steam rising from cracks in the ground, or smell sulfur carried on the breeze. These volcanic regions added another layer to the planet's character. Where the crust was thin or under stress, magma could reach the surface, creating lava flows and ash deposits. These events could be local or widespread depending on the scale of the activity. Volcanic ash settling into the oceans would bring new minerals into the water. Lava flows on land would create fresh rock that, over time, would be broken down by weathering and carried into rivers. This constant renewal of the surface kept the chemical cycles of the planet in motion. The colour of the oceans during this time may have been different as well. Today's seas often appear blue or green depending on depth and the presence of microscopic life. In the past, with different concentrations of minerals and different types of microorganisms, the water might have taken on shades that would feel unfamiliar. Some scientists suggest that parts of the ancient ocean may have had a greenish or even reddish tint at times, influenced by the chemistry of the water and the types of microbes living in it. This is difficult to confirm, but it adds another layer of strangeness to the mental picture of this ancient world. Despite all these differences, there is also a strong sense of continuity. The same sun that warms your face today warmed the surface of Penosia. The same gravity that holds you to the ground held the glaciers in place and guided the flow of rivers. The same physical laws governed the movement of air and water, the rise of heat, and the fall of rain. In that sense, this unfamiliar planet is not entirely alien. It's an earlier version of the same system you live in now, shaped by the same forces, just at a different stage in its long story. As time moved on, the balance between ice and water continued to shift. In some periods, ice advanced, spreading farther across the land and into the seas. In others, it retreated, exposing new stretches of rock and soil to the air and the elements. These cycles of advance and retreat created layers of sediment and rock that would later become part of the geological record. By reading these layers, scientists can piece together the history of climate and environment during this time, even though no written record exists. The shallow seas in particular acted like quiet archives. As sediments settled on the seafloor, they trapped the remains of microorganisms and the impressions of soft-bodied life. Over time, these layers were buried and turned into stone, preserving snapshots of a world that would otherwise be lost. It's in these ancient rocks that we find the faint outlines of early multicellular organisms, the ripple marks of long-gone waves, and the chemical signatures of past oceans. They are subtle clues, often requiring careful interpretation, but together they form a picture of a planet in transition. A world of ice that did not last forever. A world of rock that was constantly being reshaped. A world of shallow seas that offered a kind of quiet shelter for life, as it took its first tentative steps toward greater complexity. As Pannotia existed within this setting, it both influenced and was influenced by these conditions. The shape of the land affected where ice could form and how far it could spread. The position of the continents influenced how water moved and where shallow seas developed. The presence of ice and water, in turn, affected how quickly the land eroded and how the crust responded to changes in weight and pressure. This web of interactions makes it difficult to point to a single cause or effect. Instead, it's a story of feedback loops, where one change leads to another, which then circles back and influences the first. For example, when ice melts, sea levels rise, flooding low-lying areas of the continents. This creates more shallow seas, which can increase biological activity. That activity can influence the chemistry of the oceans and atmosphere, potentially affecting climate. Changes in climate can then influence how much ice forms in the first place. These are slow, subtle processes, but over millions of years they can reshape the planet. As you sit with this image of Earth during Penosia's time, it becomes clear that the planet was not waiting for something to happen. It was already alive with movement and change, even if that change was happening at a pace that feels almost still to us. The ice, the rock, and the shallow seas were not just background scenery. They were active participants in a story that would soon take a dramatic turn, as the conditions created during this period helped set the stage for a rapid expansion of life's diversity. That expansion is still ahead in the timeline, but the groundwork is being laid here, in this unfamiliar world. The minerals delivered to the oceans, the stable coastal environments, the oxygen slowly building in the air, all of these are pieces of a larger pattern that will soon become more visible in the fossil record. For now, though, the planet remains in this in-between state, not fully frozen, not fully warm, not empty, not yet crowded with life. A world of wide horizons, quiet coastlines, and slow, steady rhythms. Long before the planet settled into the quieter balance we just explored, Before shallow seas spread gently across wide shelves and ice retreated to the higher latitudes, Earth passed through a phase so extreme that it still feels almost unreal, even to the scientists who study it for a living. This was a time when cold was not just a seasonal visitor or a regional feature, but a defining presence across much of the world, a period often described with the striking name Snowball Earth. To ease into what that really means, imagine standing somewhere near the equator, a place that today would likely be warm, humid, and bright with life. Now imagine that same place covered in ice. Not just a thin layer of frost, but thick, grinding sheets of glacier stretching as far as you can see in every direction. The sun still rises and sets, but its warmth struggles to make any impression on the frozen surface. The world feels locked in a kind of slow, white stillness. This is the picture that the Snowball Earth hypothesis paints, a planet where ice may have reached from pole to pole, sealing much of the ocean beneath a frozen lid and turning the continents into vast reflective expanses of snow and glacier. The idea itself is relatively young in scientific terms. For much of the 20th century, geologists knew that ancient glaciations had occurred during the Neoproterozoic, but the scale of those ice ages was debated. It wasn't until researchers began finding glacial deposits in rocks that clearly formed near the equator that the possibility of a near-global freeze gained serious attention. These deposits include things like dropstones, large, isolated rocks embedded in fine-grained sediments. The most straightforward way to explain them is that they were carried by ice, perhaps frozen into the bottoms of glaciers or icebergs, and then dropped into the sediment when the ice melted. Finding such features in rocks that once formed in tropical latitudes suggests that ice was present far from the poles. There are also layers of rock known as diamictites, a kind of mix of sediment that looks like it was dumped in place without much sorting, often associated with glacial activity. When these appear alongside chemical signatures that point to warm, shallow marine conditions before and after, it creates a pattern that hints at dramatic swings between extreme cold and relative warmth. So how does a planet end up in a state like that in the first place? One of the key factors is something called the ice albedo feedback. Albedo is a measure of how much sunlight a surface reflects. Ice and snow are very good at reflecting sunlight back into space. Darker surfaces like open ocean or bare rock absorb more sunlight and convert it into heat. Under normal conditions, this creates a kind of balance. If the planet cools slightly and ice spreads, more sunlight gets reflected, which leads to further cooling and more ice. If the planet warms and ice retreats, more dark surface is exposed, more heat is absorbed, and warming continues. Most of the time, this feedback is moderated by other processes, such as the greenhouse effect of gases like carbon dioxide. But during the Neoproterozoic, the balance may have tipped far enough for the feedback to run away. As ice expanded from the poles toward the lower latitudes, it reflected more and more sunlight. This made the planet colder, which allowed the ice to spread even farther. Eventually, this process could have reached a point where the oceans themselves began to freeze over at the surface, even near the equator. Once a significant portion of the ocean is covered in ice, the planet enters a very different state. The exchange of heat and gases between the ocean and the atmosphere becomes limited. Weather patterns change. The water cycle slows down. At the same time, the processes that normally remove carbon dioxide from the atmosphere, such as the chemical weathering of rocks, are greatly reduced. When rock is covered by ice, rain can't easily reach it, and chemical reactions that consume CO2 slow to a crawl. Volcanoes, however, don't stop. Even in a frozen world, they continue to release carbon dioxide into the atmosphere. Over millions of years, this gas can build up, strengthening the greenhouse effect. So while the planet may be locked in ice, a slow counter process is also at work, quietly stacking the deck for a future thaw. But before we get to that turning point, it's worth lingering a little longer in the frozen world itself, because it raises a question that feels almost philosophical in nature. How does life survive on a planet like this? If the surface of the ocean is sealed beneath ice, sunlight has a hard time reaching the water below. Photosynthesis, the process that supports most of Earth's ecosystems, becomes much more difficult. The temperature of the water drops, conditions become harsh and uniform, and yet life appears to have persisted through these extreme periods. One of the key ideas is that the ice may not have been perfectly solid or uniform. Even in a global freeze, there could have been cracks, thin spots, or regions of open water, especially near volcanic areas or along coastlines where warm currents might still flow beneath the ice. Another refuge for life could have been the deep ocean. Water at depth is insulated from the surface by layers of colder water and ice above. The temperature down there remains relatively stable, hovering just above freezing. Hydrothermal vents on the seafloor, where hot, mineral-rich water emerges from the Earth's interior, create oases of warmth and chemical energy. These vents support unique ecosystems even today, independent of sunlight. Microorganisms use chemical reactions instead of photosynthesis to produce energy, forming the base of food webs that include worms, crustaceans, and other specialized creatures. During a snowball Earth, similar systems could have provided a lifeline, allowing microbial communities to persist in pockets of relative comfort while the surface of the planet remained frozen. There's also the possibility that life survived within the ice itself. In modern polar regions, scientists have found microorganisms living in tiny channels of liquid water that exist between ice crystals. These environments are extremely cold and limited, but they demonstrate that life can persist in places that seem, at first glance, completely inhospitable. So while the planet may have looked like a frozen sphere from space, beneath the surface, small, resilient forms of life were likely still carrying on, adapting to the conditions and waiting for a chance to expand again. The presence of these long global ice ages would have left a strong mark on the landscape. Glaciers are powerful agents of change. As they move, they grind down rock, smoothing mountains and carving valleys. They pick up debris and carry it along, depositing it elsewhere when they melt. This process can flatten entire regions over time, reducing highlands to rolling terrain and filling in low-lying areas with thick layers of sediment. When the ice finally retreats, it leaves behind a transformed surface. Valleys may be deepened and widened. Plains may be covered in loose material that can be easily moved by water and wind. The land becomes, in a sense, freshly reset. This reset can have important consequences for what comes next. Exposed rock weathers more easily, releasing minerals into rivers and oceans. Sediments create new shallow environments along coastlines. The chemistry of the oceans can change as a result, influencing what kinds of life can thrive. So the cold, harsh phase of Snowball Earth is not just a story of survival, it's also a story of preparation, even if that preparation is happening without any intention or direction. As the frozen world slowly accumulates carbon dioxide in its atmosphere, the balance begins to shift. The greenhouse effect strengthens, more heat is trapped. Eventually the system reaches a tipping point. When the thaw begins, it may do so quickly, at least in geological terms. Ice reflects sunlight, but as soon as patches of dark ocean or land are exposed, they start absorbing more heat. This leads to further melting, which exposes more dark surface, which leads to even more warming. The same feedback that helped freeze the planet now works in reverse. The result could be a rapid transition from global ice to a much warmer state, perhaps even a period of intense greenhouse conditions. This kind of shift would have dramatic effects. Sea levels would rise as ice melted. Massive amounts of fresh water would pour into the oceans. Weather patterns would change. The chemistry of the seas and the air would be altered by the sudden influx of materials and gases. One of the signatures of this transition is the presence of unusual layers of rock known as cap carbonates. These are thick deposits of carbonate minerals that sit directly on top of glacial sediments in many parts of the world. Their formation suggests that after the ice retreated, the oceans were suddenly saturated with carbon and calcium, leading to widespread precipitation of carbonate minerals. This points to a period of intense chemical activity in the aftermath of the thaw. It's as if the planet, after being locked in cold for millions of years, briefly swung to the other extreme, bathing its surface in warmth and chemical richness. For life, this would have been both a challenge and an opportunity. Rapid changes in temperature and chemistry can be stressful, even deadly, for many organisms, but they can also open up new niches, new ways of living, and new evolutionary pathways. Some scientists have suggested that these dramatic climate swings played a role in setting the stage for the rise of complex life. The repeated cycles of stress and recovery may have driven adaptation, encouraging organisms to become more resilient, more flexible, and eventually more complex. By the time Penosia formed, the last of the major snowball Earth events were in the past, but their influence was still felt. The continents bore the marks of glacial erosion. The oceans carried the chemical legacy of massive ice melt and subsequent weathering. The atmosphere had been reshaped by long periods of volcanic outgassing and reduced carbon removal. All of this created a world that was, in some ways, primed for change. It's also worth thinking about what this would have looked and felt like on a more human scale, even though no humans were there to experience it. Imagine a coastline where a glacier meets the sea. The ice is thick and heavy, creaking and groaning as it slowly moves forward. Chunks break off and fall into the water with deep, echoing splashes. Icebergs drift away, carrying rock and sediment frozen into their base. The water near the ice is cold and dark, but farther out, where sunlight can penetrate, the shallow sea might still host microbial life, forming thin films on the seafloor or floating near the surface. Now imagine that same coastline thousands or millions of years later, after the ice has retreated. The land is bare and wet, freshly exposed to the air. Rivers of meltwater carve new channels, rushing toward the sea. The shallow shelf is wider, fed by a constant stream of minerals and sediment. This kind of transformation, from frozen stillness to dynamic flow, would have played out across much of the planet. The term snowball Earth can sometimes give the impression of a simple, uniform state, but the reality was likely more complex. Even in a globally cold world, there would have been regional differences, variations in ice thickness, pockets of open water, and areas influenced by volcanic heat. The planet is large and varied, and even extreme conditions rarely affect every place in exactly the same way. Still, the overall effect of these ice ages was to push Earth into one of the most unusual states it has ever experienced. A state that tested the limits of its systems, from climate to chemistry to life itself. As the world moved out of these frozen chapters and into the time when Pannotia took shape, it carried with it the memory of that cold, written into the rocks, the oceans and the atmosphere. That memory influenced how the land eroded, how the seas mixed, and how life responded to its environment. It's a reminder that the planet's history is not a series of isolated events, but a continuous thread where each phase leaves traces that shape what comes next. In this case, the deep freeze of snowball Earth set the stage for a period of relative calm and stability, at least compared to the extremes that came before. That stability, combined with the changing geography of a forming supercontinent, created conditions that allowed life to begin exploring new levels of complexity. If you lift your attention away from the frozen ground and the shifting continents for a moment and let it drift upward and outward, there's another side of this ancient world waiting to be noticed. Above the ice, above the bare rock and the wide, quiet seas, there was a sky that looked familiar at first glance, blue by day, dark and star-filled by night, but carried a very different mix of air, light, and motion within it. And beneath that sky, the oceans moved and breathed in ways that set the rhythm for almost everything living on the planet at the time. The relationship between sky, sea, and air is one of Earth's oldest and most enduring conversations. During the era surrounding Pannotia, that conversation was in a particularly interesting phase, shaped by long climate swings, shifting geography, and the slow rise of oxygen that was beginning to change what life could become. Let's start with the sky itself, not just as a colour or a view, but as a layer of gases wrapped around the planet, thin and delicate when compared to the vastness of space, yet powerful enough to shape the fate of oceans, ice, and living things. The main components of the atmosphere during this time would have been familiar in name, even if their proportions were not exactly the same as today. Nitrogen still made up the bulk of the air, acting as a kind of background gas, largely inert and steady. Oxygen was present, but at lower levels than modern standards. Carbon dioxide played a more noticeable role, rising and falling over long periods depending on volcanic activity and how much of it was being absorbed by rocks and oceans. One of the most important differences between this ancient atmosphere and the one you're breathing now was the absence of land plants. Today, forests, grasslands, and even small patches of moss play a huge role in cycling carbon and oxygen between the land and the air. During Penosia's time, that entire system was missing. Instead, most of the exchange of gases happened through the oceans and through chemical reactions between air, water, and rock. Microorganisms in the sea, especially photosynthetic ones, were the main producers of oxygen. They use sunlight to split water molecules and build sugars, releasing oxygen as a byproduct. Over time, that oxygen accumulated in the atmosphere, slowly changing its composition. But this process was not smooth or steady. It was influenced by climate, by the chemistry of the oceans, and by how much oxygen could be consumed by reactions with minerals on the land and in the sea. After periods of intense glaciation, for example, freshly exposed rock could react with oxygen, pulling it out of the air and slowing its build-up. So the oxygen levels during this era likely rose in fits and starts, sometimes climbing, sometimes levelling off, sometimes even dipping slightly, depending on the balance of these processes. Even at lower concentrations, the presence of oxygen was a big deal for life. It allowed cells to use a more efficient form of metabolism, extracting more energy from the same amount of food. This extra energy could be invested in building larger bodies, more complex structures, and new ways of interacting with the environment. The sky above would also have looked a little different in terms of how it filtered sunlight. The ozone layer, which today protects the surface from much of the sun's harmful ultraviolet radiation, is made from oxygen. With lower oxygen levels, the ozone layer would have been thinner or less effective. This meant that more high-energy ultraviolet light could reach the surface, especially in shallow waters and on exposed land. For life, this posed a challenge. Ultraviolet radiation can damage DNA and other important molecules. One way around this was to stay in the water, where even a few centimetres of depth can provide significant protection. Another was to develop pigments and other chemical defences that absorb or block harmful radiation. These kinds of adaptations are still seen in many modern microorganisms, so the nature of the light itself, not just its warmth or brightness, influenced where and how life could exist. Weather patterns during this time would have been shaped by the size and shape of the supercontinent. Large land masses affect how air moves around the globe. When warm, moist air rises, it cools and releases its moisture as rain. When dry, cool air sinks, it tends to create arid conditions. With much of the land clustered together, wide interior regions of Penosia may have experienced relatively dry climates, while coastal areas and regions influenced by ocean currents could have been wetter and more moderate. The lack of vegetation also meant that the surface of the land responded more directly to changes in temperature. During the day, bare rock and sediment can heat up quickly under the sun. At night, they can lose heat just as quickly. This can lead to strong daily temperature swings, especially in dry inland areas. The air near the surface would respond to these changes, rising and falling as it warmed and cooled, creating local winds and circulation patterns. On a global scale, the contrast between warmer equatorial regions and colder polar areas would drive larger atmospheric circulation cells, much as it does today. Now, let's turn our attention downward to the oceans that covered most of the planet's surface and served as the primary home for nearly all life at the time. The oceans of this era were vast, deep, and connected in ways that depended heavily on the arrangement of the continents. With Pannotia bringing many land masses together, some ocean basins were wide and open, while others were narrowing or becoming enclosed. These differences mattered for how water moved. Ocean currents are driven by a combination of wind, the rotation of the Earth, and differences in water density caused by temperature and salinity. Warm water tends to be less dense and stays near the surface. Cold, salty water is denser and sinks. As surface water moves, it carries heat from one part of the planet to another. This can moderate climate, warming some regions and cooling others. During Penosia's time, the clustering of continents likely created large, slow-moving circulation patterns in the oceans. Some currents may have been blocked or redirected by the land, creating areas where water became trapped in circular motion. In these regions, mixing between surface and deep water could have been limited. This can lead to stratification, where layers of water with different temperatures and oxygen levels persist for long periods. The upper layers of the ocean, exposed to the atmosphere and sunlight, would have been richer in oxygen and more biologically active. The deeper layers, especially in enclosed or poorly mixed basins, might have become low in oxygen or even anoxic. These low oxygen zones present challenges for many forms of life, but they also shape the chemistry of the ocean. Certain chemical reactions occur more readily in the absence of oxygen, leading to the build-up of compounds like hydrogen sulfide or dissolved iron. Evidence from ancient rocks suggests that parts of the Neoproterozoic oceans did experience such conditions at times, especially in deeper or more restricted basins. The shallow seas along the edges of the continents, however, told a different story. These areas were generally well mixed by waves and tides. Sunlight reached the bottom, allowing photosynthetic organisms to thrive. Rivers delivered a steady supply of nutrients from the land. As a result, these coastal shelves were likely among the most productive parts of the ocean, even in a world where life was still relatively simple. Here, microbial mats could form thick layers on the seafloor, trapping sediments and creating stable surfaces. Soft-bodied multicellular organisms could spread across these mats, feeding on microorganisms or absorbing nutrients directly from the water. The chemistry of the water in these shallow zones would have been influenced by both the land and the open ocean. Fresh water from rivers mixed with salty seawater, minerals from eroding rock mixed with dissolved gases from the atmosphere. This constant mixing created environments that were chemically diverse and often more hospitable to life than the deeper, more stagnant parts of the ocean. Temperature patterns in the ocean would have been influenced by both climate and circulation. Near the equator, surface waters would generally be warmer, while polar regions and deeper layers would be colder. But the presence of ice, especially during or after snowball Earth phases, could complicate this picture. Cold, salty water formed near ice-covered regions tends to sink and spread along the sea floor, forming deep currents that can travel long distances. This process helps ventilate the deep ocean, bringing oxygen and nutrients to depths that would otherwise be cut off from the surface. If large areas of the ocean were covered by ice, this process might have been altered, potentially reducing the supply of oxygen to deeper waters in some regions while concentrating it in others. The result is a complex, shifting pattern of chemical and physical conditions across the ocean's depths. One of the most intriguing aspects of the ocean during this time is how closely its chemistry was tied to the atmosphere. Carbon dioxide from the air dissolves in seawater, forming carbonic acid, which can react with calcium and other minerals to form carbonate rocks. This process helps regulate the amount of CO2 in the atmosphere over long periods. When continents are exposed and weathering is active, more minerals are washed into the ocean, enhancing this carbon removal. When ice covers the land and weathering slows, CO2 can build up in the air. So the ocean acts as both a sink and a source for atmospheric carbon, depending on the balance of these processes. Oxygen follows a similar pattern. It dissolves into the surface waters from the air, supporting aerobic life. But it can also be consumed by reactions with organic matter and minerals, especially in deeper or stagnant waters. The distribution of oxygen in the ocean affects what kinds of organisms can live where. In well-oxygenated shallow waters, more complex life has a better chance of surviving. In low-oxygen zones, life is limited to organisms that can tolerate or exploit those conditions. This patchwork of environments creates a mosaic of habitats, each with its own challenges and opportunities. Now consider the view from the surface of the sea. If you were floating in the water during this time, you would not see schools of fish or drifting jellyfish. The surface might look quiet, perhaps broken by the occasional ripple of wind or the distant splash of ice or falling rock along a glacier-fed coast. But just beneath the surface there would be a haze of microscopic life, tiny cells suspended in the water, capturing sunlight and turning it into chemical energy. These organisms, often called phytoplankton in modern contexts, form the base of marine food webs. During this era, their ancestors and relatives played a similar role, even if the rest of the food web was much simpler. As they grew and died, their remains sank to the seafloor, carrying carbon and nutrients with them. Over time, this process helped shape the chemistry of both the ocean and the sediments below. The seafloor itself would have been a patchwork of textures and colours, influenced by sediment type, microbial activity, and the presence of early multicellular life. In some places, fine muds would settle out of calm water, forming smooth, soft surfaces. In others, coarser sands might be deposited by waves and currents, creating rippled patterns. Microbial mats could bind these sediments together, forming leathery surfaces that resisted erosion and created a kind of living skin on the bottom of the sea. The interaction between these mats and early multicellular organisms may have been an important step in the evolution of more complex ecosystems. Organisms could anchor themselves, feed, and find shelter in ways that were not possible on loose shifting sediment. Now let's bring the sky and the ocean together in the context of climate. The temperature of the planet during this time was influenced by the balance between incoming solar radiation and the heat trapped by the atmosphere. The presence of ice, the concentration of greenhouse gases, and the distribution of land and sea all played a role. When large areas of the planet were covered in ice, more sunlight was reflected back into space, cooling the planet. When ice retreated, more dark surfaces were exposed, absorbing heat and warming the system. Carbon dioxide and other greenhouse gases acted as a kind of blanket, trapping heat and moderating these swings. The oceans helped smooth out temperature differences by storing and moving heat. Water has a high heat capacity, meaning it can absorb and release large amounts of energy without changing temperature as quickly as land or air. This property made the oceans a stabilizing influence, especially in coastal regions. Even in a world that experienced extreme glaciations, areas near open water may have had more moderate conditions than the deep interior of the supercontinent. This interplay between land, sea and sky created a dynamic but interconnected system where changes in one part of the planet could ripple through the others over time. It's also worth thinking about the night sky during this era. With no artificial light, the stars would have been brilliantly visible. The Milky Way would stretch across the sky as a bright band of light. The moon would rise and set, influencing tides just as it does today. The positions of the stars would not be exactly the same as now, because the Earth's axis slowly wobbles, and the stars themselves move relative to each other over long periods. But the overall pattern of a star-filled sky would feel familiar, a reminder that even in a world of ice and bare rock, the broader universe remained unchanged. Tides, driven by the gravitational pull of the moon and the sun, would continue their steady cycle, rising and falling along the coasts of Penosia. These movements of water can be especially important in shallow seas, where they stir up sediments and mix nutrients. Tidal flats, areas that are alternately exposed and submerged, may have existed along some coastlines, creating environments with fluctuating conditions. Even without land plants or animals, these zones could host microbial communities adapted to changes in water level, salinity, and exposure to air. So when you look at the skies, oceans, and atmosphere of this time as a whole, you see a system that is both simpler and, in some ways, more raw than the one we know today. There are fewer living players, fewer complex interactions driven by plants and animals, but the fundamental processes, the movement of air and water, the cycling of gases, the influence of sunlight and gravity are all there, working together in a long, steady rhythm. This rhythm provided the backdrop for everything that followed. It shaped where life could exist, how it could grow, and what challenges it would face. Beneath the surface of those wide, quiet seas, far from the bare stone of the continents and the shifting patterns of wind and cloud above, something subtle and patient was unfolding. It didn't announce itself with sound or motion that could be seen from a distance. There were no great shapes gliding through the water, no sudden flashes of colour or speed. Instead, life during the time of Penosia moved at a scale that required closeness, stillness, and attention. A world built from cells, films, and soft forms that pressed gently against the seafloor and drifted through sunlit layers of shallow water. To step into this biological landscape, it helps to let go of modern expectations. There were no fish, no shells, no jaws, no eyes scanning the water for movement. The ocean was not yet a place of pursuit and escape. It was a place of absorption, of growth, of slow interactions between organisms and their environment. The dominant forces shaping life were chemistry, light, and the availability of nutrients, rather than competition between fast-moving creatures. At the foundation of this living world were microorganisms, especially bacteria and their close relatives. These tiny forms of life had already been shaping the planet for billions of years. They built layered communities on the seafloor known as microbial mats, which looked, in a sense, like living carpets spread across the sediment. These mats trapped particles carried by the water, binding them together and creating stable surfaces and environments that might otherwise be easily disturbed by waves or currents. Within these mats, countless chemical processes took place. Some microbes use sunlight to produce energy, releasing oxygen as a byproduct. Others use different chemical pathways, breaking down minerals or organic compounds. The mats became small, self-contained ecosystems, recycling materials and creating micro-environments where different types of organisms could find a niche. From above, a microbial mat might appear as a smooth, slightly rippled surface, sometimes forming domes or layered structures as it grew upward over time. These structures, when preserved in rock, are known as stromatolites, and they offer some of the clearest evidence of ancient life on Earth. During the time of Penosia, stromatolites were still relatively common, especially in shallow sunlit waters. Living alongside and, in some cases, on top of these microbial communities were the earliest known multicellular organisms. These were the soft-bodied forms that would later be grouped under the name Ediacaran biota, named after the hills in South Australia, where some of the first well-studied examples were found. These organisms are among the most puzzling in the fossil record. Many of them do not fit neatly into the categories we use for modern life. They don't clearly resemble animals, plants, or fungi. Some look like flat discs with radiating patterns. Others resemble fronds, anchored to the seafloor by a small base, their bodies extending upward into the water like soft, flexible leaves. Still others appear as quilted or segmented shapes, as if stitched together from repeating units. One of the reasons they are so difficult to interpret is that they did not leave behind hard parts. No bones, no shells, no teeth. Their bodies were made of soft tissue, which rarely fossilizes. What we find instead are impressions in ancient sediments, outlines pressed into layers of mud that later hardened into stone. These impressions give us shape and size, but they leave many questions unanswered. How did these organisms feed? How did they move, if they moved at all? Did they have internal organs? Did they reproduce in ways similar to modern animals? Or did they follow entirely different strategies? Some scientists suggest that many of these forms absorb nutrients directly from the water, using their large surface area to take in dissolved organic material. Others may have grazed on microbial mats, scraping or digesting the surface layer. A few could have used a combination of methods, depending on what was available. Movement where it existed was likely slow and limited. Some organisms appear to have been anchored in place, relying on water currents to bring food to them. Others may have been capable of gentle gliding or shifting across the seafloor, leaving faint traces behind. These traces, known as trace fossils, are another important window into early life. They include simple grooves, trails, and burrows preserved in sediment. Unlike body fossils, which show the shape of an organism, trace fossils show behaviour. They tell us that something moved here, fed here, interacted with the environment in a particular way. During the time of Penosia, trace fossils are relatively simple. They don't show the complex burrowing patterns or fast-directed movement seen in later periods. Instead, they suggest a world where organisms were just beginning to explore the idea of interacting with their surroundings in more active ways. The seafloor itself played a major role in shaping these interactions. Microbial mats, while providing food and structure, also created a kind of barrier. They formed cohesive surfaces that could be difficult to penetrate. For an organism trying to burrow or move beneath the surface, breaking through a mat was not a simple task. Some researchers have suggested that the presence of these mats may have slowed the development of more complex forms of movement and feeding. Only later, when organisms evolved ways to disrupt and dig through the sediment, did the seafloor become a more dynamic, three-dimensional environment. So during Penosia's time, much of life's activity was concentrated on, or just above the surface of the sediment in a relatively flat two-dimensional world. Above this layer, the water column held its own community of microscopic life. Tiny photosynthetic cells floated near the surface, capturing sunlight and forming the base of the marine food web. Other microorganisms fed on them, and so on, creating a chain of energy transfer that, while simple, was enough to support the limited diversity of larger forms present. This vertical structure of life, from sunlit surface to dimmer depths, created different zones, each with its own conditions. Near the top, light was abundant, but exposure to ultraviolet radiation was higher. Deeper down, light faded, but conditions were more stable in terms of temperature and radiation. The distribution of oxygen also varied with depth. Surface waters, in contact with the atmosphere and rich in photosynthetic activity, were more oxygenated. Deeper waters, especially in areas where circulation was limited, could be low in oxygen. These gradients influenced where different organisms could live. Some thrived in well-lit, oxygen-rich environments. Others were adapted to lower oxygen levels, relying on different metabolic pathways to survive. In this sense, even the early ocean was a patchwork of habitats, layered both horizontally across the seafloor and vertically through the water. One of the most intriguing aspects of life during this time is how little we still know about it. The fossil record is sparse and ambiguous. Soft-bodied organisms are difficult to preserve, and when they are preserved, their features are often flattened or distorted. Despite this, the sheer variety of forms suggests a period of experimentation. Evolution was trying out different body plans, different ways of interacting with the environment, different strategies for feeding and growth. Some of these experiments would leave no direct descendants. Many ediacaran forms seem to disappear from the fossil record before the Cambrian period, when a new wave of more recognizable animals appears. Whether they were outcompeted, went extinct due to environmental change, or simply evolved into forms that we no longer recognize as the same group is still a matter of debate. What is clear is that the conditions during and after Penosia's time allowed for this period of biological exploration. The combination of rising oxygen levels, abundant shallow seas, and a landscape shaped by glaciation and tectonics created a world that, while still simple, was more accommodating to larger and more complex organisms than earlier eras had been. There's also a connection here between the physical and the biological that runs quietly through this story. As glaciers melted and rivers carried sediment into the sea, they delivered not just minerals, but also organic material produced by microbial life on land and in shallow waters. This material could settle on the seafloor, providing a new source of nutrients for bottom-dwelling organisms. As continents shifted and shallow seas expanded or contracted, habitats were created and destroyed. Populations of organisms could be isolated in one region, and then, later, come back into contact with others as geography changed. This kind of separation and reunion is one of the drivers of evolutionary diversity. The slow tearing and reshaping of the land during this time was not just a geological process, it was indirectly a biological one as well. Another factor worth considering is the role of timing in all of this. The Neoproterozoic, and especially the period surrounding Penosia, comes just before the Cambrian explosion, a time when the fossil record suddenly fills with a wide variety of complex, hard-bodied animals. Some scientists have suggested that the ediacaran organisms represent an early phase of this transition, a kind of prelude where the basic possibilities of multicellular life were being explored before more robust and active forms took over. Others argue that the ediacaran biota were a unique experiment in life's history, a group that followed a different evolutionary path and eventually gave way to a new wave of organisms better suited to the changing conditions of the Cambrian world. Either way, the time of Penosia sits at a fascinating crossroads. Life had moved beyond the single-celled stage, but it had not yet developed the features we associate with modern animals, such as hard skeletons, complex organs, or active predation. The ocean, in many ways, was still a relatively gentle place, without predators that could chase, bite, or crush. The pressures shaping life were more about access to nutrients, tolerance to environmental conditions, and the ability to maintain a stable position in moving water. This does not mean the environment was easy. Changes in temperature, oxygen levels, and chemistry could still be severe. A shift in ocean circulation could alter conditions across a wide area. A change in sea level could flood or expose large regions of the seafloor. Organisms that could adapt to these changes, even in small ways, had an advantage. Consider, for example, an organism living on a shallow shelf. If sea level rose, its habitat might expand, offering more space and resources. If sea level fell, that same habitat could be exposed to the air, forcing the organism to either move, adapt, or die. Because movement was limited, adaptation often meant tolerance. Being able to survive a range of conditions rather than seeking out a specific niche could be a key strategy. This kind of generalist approach is still seen in many microorganisms today, and it may have been common among early multicellular forms as well. The question of how these organisms reproduced is another area of active research. Some may have released spores or gametes into the water, relying on currents to spread them. Others could have reproduced by budding or fragmentation, where a piece of the organism breaks off and grows into a new individual. These strategies would influence how populations spread and how genetic diversity was maintained. In a world where habitats could change over long periods, the ability to disperse or to quickly establish new populations would be valuable. There is also the possibility that some of these early organisms formed simple communities, clustering together in ways that provided mutual benefits, such as protection from currents or shared access to nutrients. Again, the fossil record gives us hints but not full answers. What we can say with more confidence is that the biological world during Penosia's time was not empty or static. It was active, varied, and in a state of gradual change. The scale of that change, however, was measured in millions of years rather than days or seasons. An entire lineage could rise, spread across shallow seas, and then fade away without leaving a clear trace in the layers of rock that survive to the present. There's a kind of quiet beauty in that. The idea that the planet hosted entire worlds of life that existed, thrived, and vanished long before any observer could notice or record them. Life remained mostly soft, small, and close to the seafloor, wrapped in a world of shallow water and gentle currents, shaped more by chemistry and light than by conflict or competition. Across the broad, pale shelves where the ancient seas met the edges of a quiet supercontinent, something was beginning to change in a way that would only become obvious much later, when layers of stone were split open and studied by curious human hands. The water still moved gently. The current still carried fine grains of sediment back and forth across the seafloor. The microbial mats still formed their soft, living skins over the mud and sand. But woven into this familiar setting was a new presence, subtle at first, then slowly more noticeable, a collection of organisms that were no longer content to remain invisible and microscopic. These were the first complex forms of life to truly make their mark on the oceans, not because they were loud or fast or aggressive, but because they were different in how they were built. Their bodies were made of many cells working together, forming shapes and patterns that could be seen, traced, and, under the right conditions, preserved. In a world that had been dominated for billions of years by single-celled life, this was a quiet but profound shift. To appreciate how significant this moment was, it helps to think about what complex really means in this context. Complexity here is not about intelligence or behaviour in the way we usually think of it. It's about organisation. It's about cells that no longer all do the same job, but instead take on different roles within a single body. Some cells might be more involved in structure, others in absorbing nutrients, others in reproduction. This division of labour allows an organism to grow larger, interact with its environment in new ways, and survive under a wider range of conditions. The seas during this time offered the space and the resources for such experiments to take shape. Shallow waters bathed in sunlight provided energy. Nutrients washed in from the land-fed microbial communities, which in turn supported larger forms. The chemistry of the oceans, influenced by rising oxygen levels, made more energy available to living cells than ever before. Against this backdrop, the first complex organisms began to stir. Many of them would not look like animals in the way we recognize today. They didn't have mouths, limbs, or eyes. Their bodies were often flat, thin, and spread out across the seafloor or gently lifted into the water by flexible stems or stalks. Some looked like simple leaves or feathers. Others resembled round pads pressed into the sediment. A few appeared as elongated, quilted shapes, their surfaces divided into repeating segments that hinted at internal organisation. These forms, known from places like Australia, Russia, Canada, and Namibia, appear in rocks that date to the later part of the Neoproterozoic, around the time Penosia existed and began to break apart. The fact that similar fossils are found on continents now separated by vast oceans is one of the clues that those land masses were once connected or much closer together. The environments where these organisms lived were usually shallow, calm marine settings. Fine sediments settled slowly, creating soft surfaces that could record impressions. When an organism died and was quickly covered by a new layer of mud or sand, its shape could be preserved long enough for the sediment to harden into rock. Millions of years later, those impressions would be revealed as fossils. What those fossils show is a community that was, in many ways, unlike anything that came before or after. Some organisms, like those known as Dickinsonia, appear as oval or elongated shapes with a series of rib-like segments radiating from a central line. Others, such as Charniodiscus, resemble fronds attached to the seafloor by a small root-like structure, their bodies extending upward into the water column. There are disc-shaped forms that may have served as anchors for frond-like bodies, or perhaps were independent organisms in their own right. There are long, ribbon-like impressions that suggest something flexible and mobile, though how much movement they actually had is still debated. One of the enduring mysteries of these early complex organisms is how they fed. Some researchers propose that many of them absorb dissolved nutrients directly from the water through their body surfaces. This would explain their flat, broad shapes, which maximize surface area. In a nutrient-rich environment, this strategy could be quite effective. Others suggest that some forms may have grazed on microbial mats, either by digesting the surface layer or by absorbing the organic material trapped within it. There is evidence in some fossil sites of disturbances in microbial mats that coincide with the presence of larger organisms, hinting at this kind of interaction. A few trace fossils from this period show simple trails or grooves in the sediment, suggesting that at least some organisms were capable of moving slowly across the seafloor. These movements would have been measured in millimeters or centimeters over long periods, rather than in the quick bursts we associate with modern animals. The appearance of even this limited movement represents an important step. Movement allows an organism to respond to its environment in new ways, to seek out better conditions, avoid less favourable ones, and interact more actively with its surroundings. The seafloor itself began to change as a result. Before the rise of more mobile life, sediments tended to settle into relatively undisturbed layers, often stabilised by microbial mats. With the introduction of organisms that could disturb the surface, even in small ways, the structure of the sediment began to shift. This process, known as bioturbation, involves the mixing of sediment by living organisms. In its early stages it was subtle, but over time it would become one of the defining features of marine environments, reshaping how nutrients and oxygen move through the seafloor. During the time of Penosia, bioturbation was still in its infancy. Most of the seafloor remained relatively flat and layered, but the first signs of disturbance were there, small hints of a more dynamic future. Another important development was the increasing role of oxygen in the ocean. As photosynthetic microorganisms continued to release oxygen, and as the chemistry of the oceans and atmosphere allowed more of it to accumulate, the amount of dissolved oxygen in surface waters rose. This made it possible for larger, more energy-demanding organisms to survive in those environments. However, this oxygen was not evenly distributed. In many deeper or more enclosed parts of the ocean, oxygen levels could still be low. This created a kind of vertical and horizontal zoning, where different forms of life occupied different layers and regions based on their tolerance for oxygen. The shallow shelves, well mixed by waves and tides, were generally the most oxygen-rich, and therefore the most hospitable to early complex life. It's no coincidence that most ediacaran fossils are found in rocks that formed in these kinds of settings. These coastal zones were also places of constant change. Sea levels rose and fell as ice advanced and retreated, and as the land itself moved up or down in response to tectonic forces. A habitat that was underwater at one point might be exposed to the air at another, and then flooded again later. Organisms living in these areas had to cope with this instability, either by being able to tolerate a range of conditions, or by spreading into new areas as old ones disappeared. This shifting geography could also isolate populations from one another. A rising land barrier or a changing coastline might cut off a group of organisms from the rest of its species. Over long periods, this isolation can lead to divergence, as different populations adapt to their local conditions in slightly different ways. So even in a world without obvious predators or complex food webs, the basic ingredients for evolutionary change were present. There's also the question of how these early complex organisms fit into the broader story of animal evolution. Some scientists see them as early branches of the animal family tree, ancestors or close relatives of modern groups. Others argue that many of them represent entirely separate lineages that evolved complex multicellular bodies independently and then went extinct without leaving direct descendants. The truth may be a mix of both. It's possible that some ediacaran forms are related to modern animals in ways that are difficult to recognise because their body plans were so different. It's also likely that others were evolutionary experiments that didn't persist into later periods. This uncertainty is part of what makes this time so fascinating. The fossil record offers a glimpse into a phase of life's history where the rules were still being written, where multiple approaches to being a complex organism were being tested at once. The lack of hard parts in these organisms also had consequences for how ecosystems functioned. Without shells or skeletons, there was less material to build reefs or other rigid structures. The seafloor remained relatively open and flat, shaped more by physical processes than by biological construction. This would change later, when organisms began to produce mineralized shells and skeletons, creating new kinds of habitats and altering how energy and nutrients flowed through marine ecosystems. But during the time we're focusing on now, the environment was still largely defined by soft surfaces and gentle interactions. Another layer to this story is the role of timing and coincidence. The rise of these early complex organisms happened around the same time that Penosia formed and began to break apart. The shifting of continents created new shallow seas and reconfigured ocean currents, influencing climate and nutrient distribution. At the same time, the planet was emerging from a series of extreme ice ages, and the chemistry of the oceans and atmosphere was in flux. All of these factors came together in a way that made this particular window of time especially favourable for biological innovation. It's not that the planet suddenly decided to produce complex life. It's that the conditions that allowed complexity to be viable and sustainable finally aligned. There's a sense of contingency in this. The idea that if things had been slightly different, if oxygen levels had risen more slowly, if ice had persisted longer, if continents had been arranged in another way, the path of life's history might have looked very different. From our vantage point hundreds of millions of years later, it's easy to see this moment as a necessary step toward the world we know. But from within that moment, it would have felt like just another phase in a long, slow and uncertain process. Consider what it would have been like to drift over one of these ancient seafloors. The water is clear enough for light to reach the bottom, but not so clear that everything is sharp and bright. The surface of the sediment is patterned with gentle ripples from past waves and currents. Here and there, soft shapes rise slightly above the surface, frond-like forms swaying almost imperceptibly in the moving water. Across the ground, thin films of microbial life give the sediment a slightly darker, perhaps even glossy appearance. In places, these films are broken or disturbed, leaving faint trails that hint at slow movement. There is no sense of urgency in this scene. Everything happens gradually. Growth, movement, decay, and burial unfold over long periods. And yet, within this calm, the seeds of a more dynamic future are being planted. As some organisms begin to move and interact with the sediment, they change the physical and chemical properties of the seafloor. Oxygen can penetrate deeper into the mud. Nutrients are mixed more thoroughly. New microhabitats form. These changes in turn create opportunities for other organisms to exploit. A slightly more oxygen-rich layer might support a new kind of metabolism. A disturbed patch of sediment might offer a place for larvae or spores to settle. This kind of feedback, where life alters the environment and the altered environment shapes life, is a recurring theme in Earth's history. During the time of Penosia, this feedback was just beginning to take on a more visible form. There is also an emotional or imaginative side to this story, even though it's grounded in science. The idea of a world where complex life is just beginning to stir, where the ocean floor hosts quiet, alien shapes that don't fit neatly into our categories, invites a sense of wonder. It's a reminder that the familiar forms of life we see today are not the only ways that living systems can organise themselves. For a long stretch of Earth's history, life followed a different set of patterns, explored different possibilities, and created ecosystems that have no exact modern equivalent. Some of those possibilities were temporary, others left subtle traces that would influence what came later. As this period draws toward its close, changes begin to accelerate. Oxygen levels continue to rise. Continental rearrangements create new coastlines and shallow seas. The chemistry of the oceans shifts in ways that favour the formation of hard parts, such as shells made from calcium carbonate or other minerals. These developments set the stage for the Cambrian period, when the fossil record suddenly becomes crowded with a wide variety of animals that look much more familiar to us, creatures with distinct heads, limbs and skeletons. But before that burst of diversity, there is this quieter phase, where complexity is present but not yet obvious in the shapes of rocks or the stories of textbooks. The first complex organisms of Pannotia's time are part of that hidden history, a bridge between a world dominated by microbes and a world filled with animals. Their legacy is not always clear in the lineages of modern life, but it is clear in the fact that complexity itself became a viable strategy. Once cells learned to cooperate, specialize and form larger bodies, there was no going back to a purely microscopic world. From that point on, life would continue to explore what could be done with size, shape and structure, leading eventually to the rich variety of forms that inhabit the planet today. Far below the quiet surfaces of ice, shallow seas and soft sediment, the planet was never truly still. Even during the coldest chapters of Earth's history, even when glaciers stretched across wide regions and life clung to narrow bands of survivable water, a deeper world of heat and motion continued its slow, persistent work. This hidden realm, buried beneath kilometres of rock and ocean, was where much of the energy that shaped Penosia's time was being generated, stored and released in ways that would eventually leave their mark on the surface. To begin understanding this restless interior, it helps to picture the Earth not as a solid, unchanging sphere, but as a layered body with very different personalities at different depths. The crust, the thin outer skin that carries continents and oceans, floats on top of the mantle, a vast region of hot, slowly moving rock. Beneath that, even deeper, lies the core, where temperatures rival those of the surface of the Sun and where the planet's magnetic field is born. The heat that rises from these depths is not just a leftover from Earth's formation. It is constantly renewed by the slow decay of radioactive elements inside the planet. This steady supply of energy keeps the mantle in motion, setting up immense currents that move over spans of millions of years. These currents, in turn, push and pull on the plates of the crust, shaping the surface in ways that are sometimes gentle and sometimes dramatic. During the time of Penosia, these deep processes were especially important because the continents were not simply sitting together in a stable arrangement. They were still adjusting to the forces that had brought them together, and they were already beginning to feel the stresses that would eventually pull them apart again. One of the most visible expressions of this hidden motion was volcanic activity. Volcanoes are, in a sense, the surface's connection to the planet's interior. They are places where molten rock, or magma, finds a pathway from deep within the mantle to the open air or the seafloor. When it reaches the surface, it cools and solidifies, creating new land or reshaping what was already there. There are different kinds of volcanoes, and during Panosia's time, many of them were likely associated with the boundaries between tectonic plates. Along subduction zones, where one plate was being forced beneath another, magma formed as the descending plate heated up and released water into the surrounding mantle. This water lowered the melting point of the rock, allowing it to melt and rise. Chains of volcanoes could form along the edges of continents, sometimes creating long arcs of fire that stretched for hundreds or even thousands of kilometers. These volcanic arcs were not just dramatic features on the landscape, they were also sources of new material. Lava flows added fresh rock to the surface. Ash settled over wide areas, blanketing land and sea with fine particles rich in minerals. When this volcanic material weathered and broke down, it released nutrients into rivers and oceans, feeding the chemical cycles that supported life in the shallow seas. Other volcanic regions formed in places where the crust was being pulled apart rather than pushed together. This is where rifts come into the story. A rift begins as a zone of tension in the crust, a place where the plates are being stretched and thinned. As the crust weakens, it can crack, forming long linear valleys. Magma from below rises into these fractures, sometimes erupting at the surface, sometimes solidifying underground and pushing the crust even farther apart. If this process continues long enough, a rift can widen into a new ocean basin, as it has in the past and continues to do today. During the era of Penosia, rifting was likely occurring in several places, even as other regions were still in the process of collision. This creates a picture of a planet that is constantly balancing between coming together and pulling apart, never settling into a single final state. Some of these rifts may have been subtle, shallow features, barely noticeable on the scale of a continent. Others could have been wide valleys, marked by volcanic activity and frequent earthquakes, places where the ground itself was being reshaped from below. The presence of ice and glaciers on the surface added another layer of complexity to this story. Ice is heavy. When thick glaciers spread across the land, they press down on the crust beneath them, causing it to sink slightly into the mantle. This process, known as isostatic loading, can change the stresses within the crust. When the ice melts and retreats, the weight is removed, and the crust can slowly rebound, rising back up over thousands of years. This movement is not smooth or uniform. It can create fractures, trigger earthquakes, and influence the flow of magma below. So even the climate of the surface world, with its cycles of freezing and thawing, had an indirect influence on what was happening deep inside the planet. In regions where ice was thick and persistent, the crust might have been pushed down, altering the pathways that magma could take as it rose. In areas where ice melted rapidly, the sudden release of pressure could encourage magma to move upward more easily, potentially increasing volcanic activity. This connection between ice and fire may seem surprising, but it highlights how interconnected Earth's systems are, even across vastly different scales and environments. Now, imagine what these processes would have looked like from the surface of Penosia. In some areas, the land would be quiet and still, covered by ice or bare rock, with little to suggest the energy moving below. In others, signs of unrest would be more obvious. You might see a line of low mountains marking a volcanic arc, their slopes built from layers of lava and ash. Steam could rise from cracks in the ground, especially where heat from below met groundwater near the surface. The air might carry a faint scent of sulfur, a reminder of gases escaping from the planet's interior. Along a rift zone, the landscape could be broken and uneven. Long, straight valleys might cut across the terrain, flanked by steep walls. The ground could be dotted with dark, hardened lava flows, their surfaces rough and jagged, still young in geological terms. Earthquakes, though likely infrequent by human standards, would have been part of the background of this world. When stresses built up in the crust and were suddenly released, the ground would shake, sometimes gently, sometimes with enough force to trigger landslides or cause sections of ice or rock to collapse. These events would not have been dramatic in the way we experience them today, because there were no cities to be damaged, no structures to fall. But they would have contributed to the ongoing reshaping of the landscape. In coastal regions, volcanic activity could extend beneath the sea. Underwater eruptions would send plumes of hot, mineral-rich water into the surrounding ocean. These hydrothermal systems created localized environments that were very different from the cold, dim waters around them. Even during periods of widespread glaciation, these vents could act as oases of warmth and chemical energy, supporting communities of microorganisms that relied on chemical reactions rather than sunlight. The minerals released by these systems, such as iron and sulfur, could also influence the chemistry of the surrounding water, sometimes creating colourful deposits on the seafloor and altering the availability of nutrients. These underwater volcanic regions were likely scattered across the ocean basins, especially along mid-ocean ridges where new crust was being formed. The ridges themselves would have been long, continuous mountain chains running through the depths, mostly hidden from view, but shaping the circulation of water and the distribution of heat and chemicals in the ocean. As magma rose and cooled at these ridges, it pushed the ocean floor apart, slowly widening the basins and contributing to the overall movement of the continents. This process, called seafloor spreading, is one of the main ways the planet renews its surface. Old crust is recycled back into the mantle at subduction zones, while new crust is created at ridges. During Penosia's time, this cycle was in full operation, even as the supercontinent existed at the surface. The balance between crust creation and destruction influenced the height of the continents and the depth of the oceans. When more crust is created, the ocean basins can become shallower, leading to higher sea levels. When more crust is destroyed, basins can deepen and sea levels can fall. These changes in sea level would have had a direct impact on the extent of shallow seas around Penosia, expanding or contracting the habitats available to early life. So once again, the deep processes of the planet fed back into the surface environment, shaping where and how organisms could live. There's also a long-term connection between volcanic activity and the atmosphere. Volcanoes release gases as well as lava and ash. Among these gases, carbon dioxide plays a particularly important role in climate. Over millions of years, volcanic emissions can build up in the atmosphere, strengthening the greenhouse effect and warming the planet. During periods of intense glaciation, when chemical weathering on land is slowed by ice cover, this volcanic input can accumulate more easily, eventually tipping the climate toward a warmer state. So the same processes that drive magma to the surface also help regulate the temperature of the entire planet. Sulfur gases released by volcanoes can have shorter-term effects as well. When they reach the atmosphere, they can form tiny particles that reflect sunlight, leading to temporary cooling. On a planet-wide scale and over long periods, these effects tend to average out, but they add to the complex interplay between geology and climate. Another aspect of this restless interior is the way it builds and reshapes mountains. When continents collide, the crust thickens and rises, forming highlands and ranges. Over time, erosion wears these down, carrying material into rivers and oceans. But even after a collision ends, the thickened crust can remain elevated for millions of years, slowly settling and adjusting to the new balance of forces. During Penosia's time, some of the mountain belts formed by earlier collisions would still have been prominent features of the landscape, while new ones were being created in other regions. These mountains influenced climate and weather by affecting how air moved across the land. Moist air rising over high terrain would cool and drop its moisture as rain or snow on the windward side, leaving the leeward side drier. They also influenced erosion patterns, controlling where rivers formed and how they flowed toward the sea. In glaciated regions, mountains served as anchors for ice sheets, places where snow could accumulate and glaciers could begin their slow descent toward lower elevations. So even the high points of the landscape were tied into the broader system of ice, water, and deep earth processes. It can be tempting to think of the planet's interior as something separate from the surface world of life and climate. But during this era, as in all others, the two were closely linked. The heat rising from below shaped the arrangement of the continents. The arrangement of the continents shaped the climate and the oceans. The climate and oceans shaped where life could exist. Life, in turn, influenced the chemistry of the atmosphere and the oceans, which fed back into climate. This chain of interactions forms a loop that runs through the entire story of Earth. From a more imaginative perspective, you can think of the planet during Penosia's time as having two distinct but connected faces. On the outside, there is a world of ice, shallow seas, and soft-bodied life, moving slowly, quietly, almost gently. On the inside, there is a world of heat, pressure, and motion, where rock flows, plates grind, and energy is constantly being transferred. The surface world may appear calm, but it is resting on a foundation that is anything but. As rifts opened and volcanoes built new land, the shape of Penosia began to change. Weak points in the crust became the seeds of future oceans. Lines of volcanic activity mark the places where the supercontinent would eventually break apart. This means that even at the height of its unity, Penosia was already carrying the blueprint of its own separation. The land did not simply drift together, and then, much later, begin to split. The processes of assembly and disassembly overlapped, happening in different regions at the same time. This gives the story a sense of motion that never truly stops. There is no stable end state, only a series of configurations that last for a while before giving way to the next. As you hold this image in mind, a planet with a calm, icy surface and a hot, restless interior, it becomes easier to see how the deep forces of geology set the stage for everything else. The shallow seas that supported early complex life existed because the crust rose and fell. The climate that allowed ice to advance and retreat was influenced by gases released from deep below. The continents that created new coastlines and habitats were moved by currents in the mantle. All of it is connected, even if the connections unfold over timescales that are hard to grasp. Not every moment in Earth's long history lingers for an equal share of time, and Penosia is a quiet example of how even something as vast as a supercontinent can pass through the planet's story more like a transition than a destination. Compared to other great gatherings of land, its period of near unity seems surprisingly brief, a span measured in tens of millions of years rather than hundreds. To understand why, it helps to look beyond the surface shape of the world and into the forces that were already working gently and persistently to pull that shape apart even as it finished coming together. One way to think about this is to imagine the continents not as rigid blocks, but as thick, floating rafts of rock, resting on a deeper layer that is warm, slow, and always in motion. These rafts can bump into one another, lock together, and form large clusters, but they never truly fuse into a single, immovable mass. The heat beneath them continues to rise and flow, and that movement creates stresses that build up over time. When Penosia formed, it did so in a world that had already been through dramatic cycles of assembly and breakup. The crust was not evenly thick or evenly strong. Some regions had been stretched and thinned by earlier rifting events. Others had been thickened and hardened by collisions and mountain building. This uneven foundation made the supercontinent more vulnerable to internal strain. As the mantle beneath continued to circulate, it pushed upward in some areas and pulled downward in others. Where hot material rose, the crust above could swell and dome upward. This stretching made it thinner and more likely to crack. Where cooler material sank, the crust could be dragged downward, creating tension along its edges. These subtle vertical movements may not have been obvious at the surface at first, but over millions of years they created lines of weakness within the supercontinent. At the same time, the sheer size of Pannotia played a role in its instability. Large landmasses act as insulating blankets over the mantle, trapping heat beneath them. This trapped heat can cause the mantle to become even warmer in certain regions, increasing the tendency for hot material to rise toward the surface. As that heat builds up, it puts pressure on the crust from below, much like steam building up under the lid of a pot. Eventually, the crust responds by stretching, cracking, and allowing magma to push upward. This process can begin in small ways, with localized volcanic activity and the formation of shallow rift valleys. Over time, if the stress continues, those rifts can widen and deepen, setting the stage for the formation of new ocean basins. So even while Penosia existed as a single connected landmass, the conditions that would lead to its breakup were already being created by the heat and motion beneath it. Another factor that influenced the supercontinent's short lifespan was the way it interacted with the oceans and the climate. When continents come together, they change the patterns of ocean circulation. As we've explored, this can affect how heat is distributed around the globe. During Panosia's time, the clustering of land likely contributed to strong temperature contrasts between different regions. In some areas, ice persisted, especially toward the poles and in higher elevations. In others, shallow seas and coastal zones experienced warmer, more stable conditions. These contrasts influenced erosion and sedimentation patterns. In colder regions, glaciers ground down the land and delivered large amounts of debris to the sea. In warmer, wetter areas, rivers carried sediments from eroding mountains and plains into the shallow shelves. All of this material built up along the edges of the supercontinent and in nearby basins. The weight of these thick sediment piles could press down on the crust, causing it to sink slightly. This added another layer of stress to the system, especially in regions where the crust was already thin or weakened. Sea level changes driven by the advance and retreat of ice, as well as by the creation and destruction of oceanic crust, also played a role. When sea levels rose, shallow seas flooded low-lying areas of the land, adding weight in the form of water. When sea levels fell, that weight was removed. These changes may seem small compared to the scale of continents, but over large areas and long periods, they can influence how the crust flexes and responds to deeper forces. There's also the matter of timing. Penosia formed at a moment when the planet was emerging from extreme climatic conditions and moving toward a period of increasing biological activity. The same processes that helped create more favourable conditions for life, such as increased weathering of rocks and the delivery of nutrients to the oceans, also contributed to the chemical and physical changes that affected the crust. Weathering, for example, doesn't just shape the surface, it alters the composition of rocks, weakening them over time. In regions where the crust had already been stretched or fractured, this chemical weakening could make it easier for rifts to develop. The rising levels of oxygen in the atmosphere and oceans also played a subtle role. Oxygen can react with certain minerals, changing their structure and strength. While this is a slow process, over millions of years, it can influence the mechanical properties of the crust in specific regions. So the environment above and the processes below were working together in indirect ways to create conditions that favoured change rather than stability. Another important piece of the puzzle is the way that supercontinents influence the flow of heat from the mantle. When land is spread out across the globe, heat can escape more evenly. When it's clustered together, large areas of the mantle are covered by thick, insulating crust. This can lead to the development of what are sometimes called mantle plumes, columns of hot material that rise from deep within the earth toward the surface. If one of these plumes reaches the base of the crust, it can cause widespread melting and volcanic activity. It can also lift the crust upward over a broad area, creating a kind of dome. As the crust is lifted, it stretches, cracks form, magma fills those cracks. Over time, these features can link up into long rift systems. Some scientists think that mantle plumes played a role in initiating the breakup of Penosia, just as they may have contributed to the breakup of other supercontinents at different times in Earth's history. These plumes don't need to be especially dramatic at the surface to have a significant effect. Even a slow, steady upwelling of hot material can, over millions of years, weaken and thin the crust enough to tip the balance toward separation. While all of this was happening internally, the external shape of the supercontinent also mattered. Pannotia was not a compact, evenly shaped mass. It likely had long, irregular coastlines and deep embayments of ocean cutting into it. These features can act as stress concentrators, places where the forces within the crust are focused rather than evenly distributed. Think of how a piece of paper is easier to tear if it already has a notch or a cut. The irregular edges of Penosia may have served a similar role, making it easier for rifts to form and propagate from existing indentations and weak points. These embayments also influenced how water moved into and out of the supercontinent. Shallow seas could penetrate far inland, bringing with them the weight of water and thick layers of sediment. This added load could further stress the crust beneath. The role of plate boundaries is also important to consider. Not all parts of Penosia were equally stable or equally connected. Some regions were held together by strong, recently formed mountain belts. Others were linked more loosely, perhaps by narrow strips of land, or by areas of crust that had not yet fully stabilised after earlier tectonic events. These loosely connected regions would be natural candidates for the first places to break apart. Once a rift begins in one area, it can influence the stress distribution across the entire supercontinent. The opening of a new rift can change the direction and magnitude of forces elsewhere, sometimes triggering additional rifting in distant regions. This kind of chain reaction can accelerate the breakup process, turning what might have been a slow, localised change into a more widespread reorganisation of the land. There's also a sense in which Penosia's short lifespan reflects the broader rhythm of Earth's tectonic cycle. The planet seems to go through phases where supercontinents form and then break apart, roughly every few 100 million years. This cycle is driven by the way heat builds up beneath large land masses and is then released through rifting and seafloor spreading. Pannotia appears to have formed near the end of one of these cycles and begun to break apart near the beginning of the next. In that sense, it occupies a kind of in-between position, a moment of transition rather than a long period of stability. This transitional role may help explain why its geological signature is less pronounced and more difficult to trace than that of longer-lived supercontinents like Pangaea or Rodinia. Because Penosia did not persist for as long, there was less time for thick, extensive layers of sediment to build up across its interior. There was less time for massive, continuous mountain belts to develop and be preserved. The traces it left behind are more fragmented, scattered across different continents that have since travelled far from one another. For scientists, this makes reconstructing Penosia a kind of detective story, piecing together clues from rocks that were once neighbours but are now separated by oceans. From a more reflective perspective, there's something almost poetic about this fleetingness, even if we're avoiding poetic language in the narration itself. The idea that a supercontinent, something that feels like it should be permanent and unchanging, can come together and then quietly drift apart in what amounts to a relatively short geological moment, serves as a reminder of the scale at which the planet operates. What feels vast and enduring to us can be just a passing phase in Earth's own timeline. As Penosia began to fragment, the changes would not have been obvious at first. A small rift here, a line of volcanoes there, shallow seas slowly widening, new stretches of coastline forming where land had once been continuous. Over millions of years, though, these small changes would add up. The supercontinent would lose its coherence. Pieces of land would begin their own independent journeys across the surface of the planet, carried by the same slow-moving plates that had once brought them together. This breakup would reshape ocean circulation, alter climate patterns, and create new habitats for life. It would help set the stage for the dramatic biological expansion that followed in the Cambrian period. So in a sense, Penosia's short lifespan was not a failure or an anomaly. It was part of a larger process, a necessary step in a cycle that moves the planet between unity and diversity, between gathering and dispersal. From the outside, it might have looked like nothing was happening at all. The coastline still traced their long, uneven paths along the edges of the land. The shallow seas still spread gently across wide shelves. The ice still clung to colder regions, and the early life in the oceans continued its slow, quiet routines. But beneath this calm surface, the shape of the world was beginning to change in a way that would eventually redraw the map of the planet. The separation of a supercontinent does not begin with a dramatic split or a visible gap you could point to and say, here it starts. Instead, it begins as a subtle feeling of tension in the crust, a deep, persistent stretching that builds over millions of years. Rock that once sat comfortably in place starts to thin. Tiny fractures form far below the surface, long before any valley or sea appears above. These early stages often take place in regions that were already weakened by earlier events, areas that had been stretched in the past or compressed and thickened by mountain building, tend to hold hidden faults and zones of weakness. When new stresses are applied, these are the places most likely to respond. During the time when Penosia began to lose its unity, the mantle beneath the supercontinent continued to deliver heat upward. In some regions, this heat caused the crust to rise slightly, forming broad, gentle domes. This uplift was not like the sharp peaks of mountain ranges. It was subtle, spread across hundreds or even thousands of kilometers. As the crust rose, it also stretched. Imagine lifting the center of a thick piece of dough. The top thins and begins to crack even if the edges remain intact. In a similar way, the rising crust above a warm region of the mantle began to fracture. Magma from below took advantage of these fractures. It moved upward, sometimes cooling and solidifying underground, sometimes erupting at the surface as lava. Each intrusion of molten rock pushed the surrounding crust a little farther apart, widening the cracks. Over time, these cracks linked up, forming long, linear features known as rift zones. A rift zone is the early blueprint of a future ocean. It often begins as a valley, flanked by slightly raised shoulders where the crust has been stretched and thinned. The floor of the valley can sink as material moves away beneath it, creating space that is sometimes filled by lakes, shallow seas, or lava flows. During Penosia's breakup, several such rifts likely developed across different parts of the supercontinent. They did not all appear at once, and they did not all follow the same pattern. Some may have been short-lived, stalling, and eventually closing again. Others continued to widen, becoming the seeds of new ocean basins. As these rift zones formed, they would have changed the surface environment in noticeable ways. The land along a rift could become lower than the surrounding terrain, allowing water to collect. In some cases, rivers would flow into these low areas, creating long, narrow lakes or inland seas. In others, if the rift connected to the global ocean, seawater could flood in, forming a shallow, linear sea that cut deep into the supercontinent. These new bodies of water created fresh coastlines, which in turn created new shallow marine habitats. For the early life of the oceans, this meant new places to settle, grow, and diversify. At the same time, the volcanic activity associated with rifting added heat and minerals to the environment. Lava flows could cover wide areas of land, creating fresh rock surfaces that would later be broken down by weathering. Ash and volcanic gases could enter the atmosphere, influencing climate on local or even regional scales. The presence of magma near the surface also affected groundwater. Heat could drive the circulation of water through cracks in the rock, creating hot springs and hydrothermal systems. These environments, rich in dissolved minerals and heat, offered unique niches for microorganisms, much like the hydrothermal vents on the ocean floor. While the rifts were opening in some areas, other parts of the supercontinent were still adjusting to the collisions that had brought Penosia together in the first place. Mountain belts formed during those earlier collisions did not simply vanish when rifting began elsewhere. Instead, they continued to influence how the land responded to new stresses. Thickened crust in these regions could resist stretching more strongly, causing rifts to form around or alongside them rather than cutting straight through. This created a complex pattern of separation, where the supercontinent did not split neatly down the middle, but instead broke apart along curved, branching lines that followed the path of least resistance. As time went on, some of these rifts widened enough that the crust between the two sides became very thin. Eventually it could rupture completely, allowing magma from the mantle to reach the surface along a long continuous line. When this happens beneath the ocean, it forms a mid-ocean ridge, a place where new oceanic crust is created as magma rises, cools, and spreads outward. Once a ridge is established, the two sides of the former supercontinent are no longer just drifting apart. They are being actively pushed away from each other by the creation of new crust between them. This marks a major transition. What was once a rift valley or a narrow sea becomes a growing ocean basin. During the breakup of Penosia, this process would have been in its early stages. The oceans that formed were not yet the vast, deep bodies of water we know today. They began as shallow, widening gaps that slowly filled with water and new crust. The rate of this separation was still slow by human standards. The continents moved at speeds measured in centimetres per year. But over millions of years, those centimetres added up to hundreds and then thousands of kilometres. As the land drifted apart, the shape of the global ocean changed. New circulation pathways opened up. Water that had once been confined to certain regions could now flow between basins. Currents shifted, carrying heat and nutrients along new routes. These changes had a direct impact on climate. Regions that were once warmed by certain currents might cool as those pathways were altered. Other areas might become warmer or wetter as new currents brought in heat and moisture. The atmosphere responded as well. Changes in sea surface temperatures can influence wind patterns and the formation of storms. The redistribution of land and sea alters how air moves around the globe, so the slow tearing apart of Penosia was not just a geological event, it was a planetary one, with consequences that rippled through the climate system and into the living world. For life in the oceans, the creation of new coastlines and shallow seas was especially significant. Shallow marine environments are often among the most productive and diverse. They receive sunlight, nutrients from the land, and mixing from waves and tides. As new rifts opened and flooded, they created long stretches of fresh habitat. Populations of organisms that had once been part of a continuous coastal community could become separated by widening seas. Over time, this isolation could lead to divergence, as different groups adapted to their local conditions. At the same time, new connections between ocean basins could allow organisms to spread into regions they had not previously occupied. This mixing of life from different areas can also drive evolutionary change, introducing new interactions and pressures. So the breakup of a supercontinent tends to increase the diversity of environments, and, often, the diversity of life. On land, even though complex life had not yet established itself in the way it would later, the changes were still profound. Rifting created low-lying regions that could trap water and sediment. Volcanic activity reshaped large areas of the surface. The movement of the crust influenced the flow of rivers, redirecting them into new basins or toward new coastlines. Erosion worked on the freshly exposed rock, carrying material into the seas and altering the chemistry of the water. All of these processes fed back into the ocean system, reinforcing the link between deep Earth activity and surface environments. It's also worth thinking about how this slow separation would have felt if you could somehow observe it over time. In a single human lifetime, you would see almost nothing. The land would look the same from year to year. The coastlines would not visibly change. The mountains would not move. But if you could watch over 1,000,000 years, you might notice a valley deepening, a line of volcanoes becoming more active, a narrow sea slowly widening. Over 10 million years, a continuous stretch of land might break into two distinct pieces, separated by a body of water that continues to grow. This kind of perspective highlights the difference between the timescales of human experience and the timescales of the planet. The Earth's changes are not usually sudden. They are patient, persistent, and cumulative. The story of Penosia's breakup is, in many ways, a story of accumulation. Small movements, small cracks, small eruptions, all adding up over vast stretches of time to create a completely different arrangement of the world. There's also a sense of inevitability in this process. Once a rift has developed and a new ocean basin has begun to form, it tends to continue. The creation of new crust at a ridge pushes the continents farther apart, which allows more magma to rise, which creates more crust, which pushes them even farther apart. This positive feedback can keep a separation going for tens or even hundreds of millions of years. Of course, not all rifts succeed. Some fail, becoming what geologists call erosions, rift arms that start to open but then stop. These features can remain as scars in the crust, long linear basins that never become full oceans. During Penosia's time, there may have been a mix of both successful and failed rifts, adding to the complexity of the supercontinent's breakup pattern. As the land continued to fragment, the identity of Penosia as a single, unified mass gradually faded. What remained were a series of large continental blocks, each beginning its own journey across the surface of the planet. Over time, these blocks would become the ancestors of the continents we recognize today. Their paths would take them through different climates, across different latitudes, and into new collisions and separations that would shape the next phases of the Earth's history. The oceans between them would grow deeper and wider, developing their own systems of currents, ecosystems, and chemical cycles. From a broader perspective, this moment marks a shift from unity to diversity, not just in the arrangement of land, but in the range of environments available across the planet. A single supercontinent tends to create large interior regions with similar conditions. A world of multiple continents creates more coastlines, more shallow seas, and more varied climates. This diversity of settings can support a greater diversity of life. So the slow tearing apart of Pannotia, while it represents the end of one configuration of the world, also represents the opening of new possibilities. It's a reminder that in Earth's story, endings and beginnings are often the same event viewed from different angles. Long after the land that once formed Penosia had begun to drift into separate pieces, the planet entered a phase of biological change so noticeable in the fossil record that it almost feels sudden when viewed from the present. This is the period known as the Cambrian, a stretch of time when the oceans filled with a wide variety of animals that had hard parts, distinct body plans, and new ways of interacting with their environment. The appearance of these forms, often called the Cambrian explosion, didn't come out of nowhere. It was shaped, in quiet and indirect ways, by the earlier existence and breakup of that short-lived supercontinent. To see how these two stories connect, it helps to think of Penosia not as a finished chapter that closed neatly, but as a set of conditions that continue to influence the world even after the land itself had changed shape. The movement of continents, the creation of new coastlines, the reshaping of oceans, and the chemical legacy left behind by glaciation and volcanism all fed into the environment that early Cambrian life encountered. One of the most important links between Penosia and the Cambrian world lies in geography. When a supercontinent breaks apart, it increases the total length of coastlines across the planet. Instead of one large landmass with a relatively limited perimeter, the world becomes a collection of continents and smaller land fragments, each surrounded by water. This creates many more shallow marine environments, which are often the most biologically productive parts of the ocean. Shallow seas allow sunlight to reach the sea floor. They receive nutrients from the land through rivers and coastal erosion. They are mixed by waves and tides, which helps distribute oxygen and minerals. As Penosia fragmented, these kinds of environments became more widespread. New continental shelves formed along the edges of the drifting land masses. Inland seas and narrow straits opened between separating blocks of crust. Each of these settings offered a slightly different combination of temperature, depth, chemistry, and circulation. Together, they created a patchwork of habitats where different forms of life could find opportunities to thrive. This increase in environmental diversity is one of the key ingredients for biological diversification. When populations of organisms are spread across a variety of settings, they face different challenges and pressures. Some might live in warmer, well-lit waters, others might occupy cooler, deeper zones. Some might experience steady conditions, while others deal with frequent changes in water level or chemistry. Over time, these differences can lead to the development of new traits and eventually new species. The more varied the environments, the more pathways there are for life to explore. So the breakup of Penosia, by reshaping the world's geography, helped create a stage that was much more complex than the one that existed when the land was unified. Another important connection involves the chemistry of the oceans. As the continents moved and new rifts opened, volcanic activity continued to supply minerals and gases to the surface. At the same time, erosion of newly exposed rock delivered a steady stream of nutrients into the seas. These inputs influenced the availability of key elements such as calcium, phosphorus, and iron, all of which play roles in biological processes. Calcium, in particular, is important because it is a major component of many hard parts, such as shells and skeletons. The Cambrian period is marked by the widespread appearance of organisms that produced mineralized structures. The reasons for this shift are still debated, but one factor may have been the changing chemistry of the oceans, which made it easier for organisms to extract and use minerals from seawater. The aftermath of snowball Earth events also played a role here. The melting of global ice and the intense weathering that followed would have delivered large amounts of dissolved minerals to the oceans. This could have increased the concentration of certain ions in seawater, creating conditions that favoured the precipitation of minerals. In such an environment, Organisms that evolved ways to control and harness these chemical processes could gain advantages. Hard parts can provide protection, support, and new ways of interacting with the environment. So the geological and climatic history tied to Penosia set the chemical stage for one of the most visible features of the Cambrian world. Oxygen is another part of this story. As we've explored earlier, oxygen levels in the atmosphere and oceans were rising during the late Neoproterozoic. This trend likely continued into the Cambrian. Higher oxygen levels allow organisms to sustain higher metabolic rates. This supports more active lifestyles, larger body sizes, and more complex internal structures. The increase in shallow, well-mixed seas following the breakup of Penosia would have helped distribute oxygen more effectively in coastal environments. Waves, tides, and currents promote the exchange of gases between the air and the water, keeping surface waters oxygen-rich. These conditions would have been especially favourable for organisms that relied on oxygen for efficient energy production. So once again, the changing shape of the land influenced the chemistry of the sea, which in turn influenced what kinds of life could exist there. There is also a more subtle connection related to the physical structure of the seafloor. During the time when life was mostly soft-bodied and microbial mats were common, the seafloor tended to be relatively flat and stable. Sediments settled in layers and the mats bound them together. As organisms began to move more actively and disturb the sediment, the structure of the seafloor changed. This process, which we touched on earlier, gradually turned the seafloor into a more three-dimensional environment, with burrows, tunnels, and mixed layers. The expansion of shallow marine environments after Penosia's breakup would have accelerated this transformation. More coastline means more places where organisms can interact with the sediment. More diverse habitats mean more opportunities for different strategies of living. As burrowing and movement became more common, the seafloor became oxygenated at greater depths. This changed the chemistry of the sediment, making it possible for new kinds of organisms to live there. This feedback between biology and geology, where life alters the physical environment and the altered environment supports new forms of life, is a hallmark of the Cambrian period. The timing of continental drift also influenced how populations were distributed. As land masses separated, they carried their coastal ecosystems with them. Populations that had once been connected could become isolated by widening seas. Over long periods, this isolation can lead to divergence, as different groups adapt to their local conditions. At the same time, the opening of new seaways allowed currents to carry larvae and other small organisms between regions that had previously been cut off. This combination of isolation and connection is a powerful driver of evolutionary change. It creates both the separation needed for diversification and the mixing needed for competition and innovation. So the drifting pieces of Penosia helped set up a global system where life could spread, adapt, and diversify on a larger scale than before. There is also the influence of climate stability to consider. While the Neoproterozoic was marked by extreme swings between global ice and warmer conditions, the early Cambrian appears to have been relatively more stable in many regions, at least compared to those earlier extremes. The arrangement of continents after Penosia's breakup may have contributed to this stability by allowing ocean currents to circulate more freely around the globe. This can help distribute heat more evenly and reduce the likelihood of runaway cooling or warming in specific regions. A more stable climate does not mean a static one, but it can provide a more predictable range of conditions over long periods. For life, this kind of predictability can make it easier to invest in more specialized adaptations, rather than just focusing on survival through extreme changes. Specialization, in turn, can lead to greater diversity as different organisms evolve to exploit different niches. Another piece of the puzzle is the role of sedimentation. As the continents broke apart and new coastlines formed, erosion continued to deliver large amounts of sediment to the seas. These sediments created new layers on the seafloor, building up thick deposits over time. These deposits could bury and preserve the remains of organisms, contributing to the richer fossil record of the Cambrian period. But they also shaped the physical environment in which those organisms lived. Soft, muddy bottoms, sandy shelves, and rocky coastlines each offered different challenges and opportunities. The variety of sediment types created by the changing geography added another layer of habitat diversity. Some organisms might adapt to burrow in soft mud. Others might attach themselves to firmer substrates. Still others might live in the spaces between sand grains. So even at the level of the seafloor's texture, the legacy of Penosia's breakup can be felt. It's also worth thinking about the psychological or conceptual impact of the Cambrian explosion in how we interpret Earth's history. From our perspective, it looks like a sudden burst of life, but when you trace the chain of events backward, you see a long build-up of conditions, many of which are tied to processes that began well before the Cambrian itself. Penosia's formation and breakup are part of that build-up. They influence climate, chemistry, geography, and circulation patterns. They shape the distribution of shallow seas and the availability of nutrients. They affected oxygen levels and the physical structure of marine habitats. None of these factors alone can fully explain the Cambrian explosion, but together they form a web of influences that made such a transformation possible. There is also an element of timing that is difficult to separate from chance. The alignment of rising oxygen levels, favourable ocean chemistry, diverse habitats, and a relatively stable climate may not have happened at many other points in Earth's history. That it happened when it did is part of what makes the Cambrian period stand out so strongly in the fossil record. If Penosia had lasted longer, keeping the land more unified, the distribution of shallow seas might have been more limited. If it had broken apart earlier, the chemical and biological conditions might not have been ready for complexity to flourish in the same way. So the particular timing of its existence and breakup may have been just as important as the processes themselves. From a broader view, this highlights a theme that runs through the planet's story. Earth's history is not just a sequence of independent events. It is a network of interconnected processes where changes in the deep interior influence the surface, where the shape of the land influences the flow of water and air, where the chemistry of the environment influences what life can become. Penosia sits at a point in that network where many threads come together. Its formation was tied to the movement of plates and the flow of heat from the mantle. Its environment was shaped by global glaciation and the recovery from it. Its breakup influenced the distribution of oceans and the circulation of currents. All of these threads fed into the conditions that allowed life to take a dramatic step forward. As the Cambrian period unfolded, the oceans became home to animals with hard shells, jointed limbs, complex eyes, and a wide range of feeding strategies. Predation became an important force, driving further adaptation and innovation. The quiet, mat-covered seafloors of earlier times gave way to more dynamic environments, with burrows, reefs, and complex food webs. The world began to look, in a very general sense, more like the one we recognise today. But even as this transformation took place, the deeper rhythms of the planet continued. Continents kept drifting. Mountains kept rising and eroding. Oceans kept opening and closing. The legacy of Penosia did not end with the Cambrian explosion. The arrangement of land and sea that followed would continue to influence climate and life for hundreds of millions of years. Some of the continents that broke away from Penosia would later collide again, forming new supercontinents and restarting the cycle of unity and separation. So in this story, the Cambrian explosion is not a final destination. It is another phase in a long, ongoing process. The connection between Penosia and the rise of complex life serves as a reminder that biological change is deeply tied to geological change. Life does not evolve in a vacuum. It evolves on a moving, changing planet, one where the ground beneath and the air above are always part of the equation. From a distance, it can seem as though Penosia simply appeared, lingered for a brief moment in the deep past, and then slipped away, leaving only faint traces in the rocks and in the shifting outlines of continents. But when you look more closely, the world that followed carried with it a set of changes that did not fade. The planet gained more than a memory of a supercontinent. It gained new patterns, new balances, and new possibilities that continued to shape the surface, the oceans, the air, and the living systems that would grow upon them. To understand what Earth gained, it helps to think in terms of layers, not just of rock, but of influence. At the most basic level, there is the physical layer, the shape of the land and the structure of the crust. The formation and breakup of Penosia left behind a rearranged map of continents that would guide the movement of plates for hundreds of millions of years. Fault lines, mountain belts, and zones of thickened or thinned crust became part of the planet's long-term framework. When a supercontinent forms, the collisions between landmasses create deep, complex structures in the crust. Rocks are folded, stacked, and sometimes pushed far below the surface before being uplifted again. These ancient collision zones can remain mechanically strong or weak long after the mountains they formed have been eroded away. In the case of Penosia, some of these deep structures likely influence where later rifts would form and where future continents would collide. The planet does not start with a blank slate after each cycle of assembly and breakup. It builds on what came before. So one of the lasting gains from this forgotten world was a kind of geological memory, a set of internal patterns that guided how the surface would continue to change. There is also the way the breakup of Penosia contributed to the expansion of the oceans. As the land separated, new basins formed and widened. These basins did not just fill with water, they developed their own systems of ridges, trenches, and currents. Over time, they became part of the global ocean network that moves heat, nutrients, and gases around the planet. This network is one of the key regulators of climate. It helps distribute warmth from the equator toward the poles, and brings cold water back toward lower latitudes. It influences where ice can form, where rain falls, and where dry regions develop. By increasing the number and complexity of ocean basins, the breakup of Pannotia helped create a more interconnected and dynamic ocean system. This in turn fed back into the atmosphere. The oceans and the air are in constant exchange. Carbon dioxide dissolves into seawater and can be stored in sediments. Oxygen produced by marine life enters the atmosphere. Heat moves between the two, shaping weather and climate. A more complex ocean system means more pathways for these exchanges to occur. It means more regions where warm water can rise and release heat into the air, and more areas where cold water can sink and draw heat away. So one of the planet's gains was a more finely tuned climate engine, one capable of moderating conditions across a wide range of latitudes and environments. On the surface, the expansion of coastlines and shallow seas created a new kind of world. Shallow marine environments are among the most influential in Earth's history, not just for life, but for chemistry and geology as well. These areas are where land and sea meet, where rivers deliver sediments and nutrients, where waves and tides stir the water and the seafloor, and where sunlight can reach the bottom. The increase in these environments after Penosia's breakup meant more places where rock could weather, where minerals could be released, and where chemical reactions between water, air, and stone could take place. Over long periods, this kind of activity influences the composition of seawater and the atmosphere. It affects how much carbon is locked away in sediments and how much remains in the air as carbon dioxide. So another gain was a more active interface between land and sea, a broader zone where the planet's major chemical cycles could operate. This chemical legacy is closely tied to the story of life. The minerals delivered to the oceans by erosion, including calcium, phosphorus, and trace elements, are essential for biological processes. They support the formation of shells and skeletons, the construction of cell membranes, and the chemistry of energy transfer within living cells. As these materials became more widely available in the seas, they supported the expansion of more complex ecosystems. The timing of this availability, following the breakup of Penosia and the changes in ocean circulation that came with it, helped shape the path life would take in the Cambrian and beyond. But the gain was not just in materials, it was in structure. The increase in shallow seas created more layered habitats, with different conditions at different depths and distances from shore. Light, temperature, oxygen, and nutrient levels could vary over relatively short distances. This variation creates niches, places where organisms with specific adaptations can thrive. The more niches there are, the more ways life can diversify. So in a very real sense, the planet gained complexity in its living spaces, not just in its living forms. There is also a quieter gain to consider, one that is written into the sediments themselves. As Penosia broke apart and new basins formed, thick layers of sediment accumulated in many regions. These sediments did more than just preserve fossils. They stored chemical records of the environment. The ratios of different isotopes in these rocks tell us about past temperatures, ocean chemistry, and atmospheric composition. They record shifts in climate and in the cycling of elements like carbon and sulfur. From the planet's perspective, this is a kind of archive, a long-term storage of information about its own history. This may sound abstract, but it has practical consequences. The presence of thick sedimentary basins influences how the crust behaves. These basins can be zones of weakness where future rifting is more likely to occur. They can also be places where heat is trapped or released differently than in surrounding regions. So even the layers of mud and sand laid down in the aftermath of Penosia's breakup became part of the planet's evolving structure. Looking upward, the atmosphere also carries the imprint of this ancient world. The gradual rise of oxygen that continued through this period transformed the chemistry of the air. This had immediate effects on life, as we've discussed, but it also changed how the planet interacts with sunlight. Oxygen in the upper atmosphere forms ozone, which absorbs much of the sun's harmful ultraviolet radiation. A stronger ozone layer means more protection for life at the surface and in shallow water. This, in turn, makes it easier for organisms to explore new environments, including those closer to the air and, eventually, onto land. So one of the planet's gains from this period was a more protective atmospheric shield, a subtle but powerful change that would influence the future course of life's expansion. The presence of more oxygen also altered the way rocks weather. Oxidation reactions can change the colour, composition, and strength of minerals. Over long periods, this influences how landscapes erode and how sediments are formed. So the land itself, in terms of its surface appearance and behaviour, began to take on characteristics that are more familiar to us today. There is also a gain that is less tangible, but just as important: the establishment of feedback loops that would continue to operate in more complex ways. By the time Panosia's legacy was fully unfolding, the planet had a system where life, climate, and geology were deeply intertwined. Life influenced the atmosphere by producing oxygen and affecting carbon cycles. The atmosphere influenced climate. Climate influenced erosion and ocean circulation. Erosion and circulation influenced the availability of nutrients for life. These loops existed before, of course, but the scale and intensity of them increased as life became more complex and as the geography of the planet became more varied. So Earth gained a more tightly coupled system, one where changes in one part of the planet could more easily ripple through the rest. This kind of coupling can make a system more resilient, but it can also make it more sensitive. A change in climate, for example, can alter erosion patterns, which can change ocean chemistry, which can influence life, which can then feed back into the atmosphere. This sensitivity would become a defining feature of the planet's later history, including periods of rapid warming, cooling, and biological turnover. Another aspect to consider is the role of time itself. Penosia's relatively brief existence left behind a world that was, in many ways, primed for change rather than stability. The continents were already in motion, the oceans were reorganizing, the climate system was adjusting to new patterns of circulation and heat distribution. This state of motion may have made the planet more open to innovation, both geological and biological. A world that is constantly shifting creates challenges, but it also creates opportunities. New habitats appear. old ones disappear, connections form and break. Life that can adapt to this kind of dynamism has a chance to expand into new roles. So one of the planet's gains from this period was a kind of momentum, a push toward a more active and varied surface world. There's also a perspective that looks at what Earth gained in terms of narrative, not in a human storytelling sense, but in the way its history is structured. Penosia sits at a point where several major threads come together: the end of extreme global glaciations, the rise of more complex life, and the reorganization of continents into a more familiar pattern. Because of this, it acts as a bridge between very different kinds of worlds. Before it, the planet is dominated by microbes and extreme climates. After it, the planet enters an era of animals, complex ecosystems, and more recognizable geography. The gains of this period are, in a way, the foundations of that later world. It's also interesting to think about what did not happen, and how that absence itself shaped the future. Penosia did not last long enough to develop a vast, stable interior like some other supercontinents. It did not create a single, massive desert or a single, continuous climate zone across much of the land. Instead, its breakup led fairly quickly to a world of multiple continents and varied coastlines. This may have prevented the development of some of the extreme conditions seen during the long-lived supercontinent phases later in Earth's history. So the planet gained, in relative terms, a more varied and possibly more moderate range of surface environments. Another long-term gain is seen in the way future supercontinents would form. The fragments of Penosia didn't wander randomly. Their paths were influenced by the structures left behind in the crust and mantle. Some of these fragments would later come back together in new configurations, contributing to the formation of supercontinents like Gondwana and, much later, Pangaea. So Penosia's existence and breakup became part of a larger cycle, one that continues to shape the planet today. Each cycle builds on the last, carrying forward the effects of earlier arrangements. From a biological perspective, the gains are perhaps the most visible. The period following Penosia saw the expansion of ecosystems that included not just microbes and soft-bodied organisms, but animals with hard parts, complex behaviours, and intricate interactions. The food webs became more layered. Predation became a driving force. The physical environment became more actively shaped by living things through reef building, burrowing, and the production of shells and skeletons. All of this traces back in part to the conditions that emerged from Penosia's legacy. The planet gained a living surface that was no longer just a passive stage for life, but an active participant in shaping it. There's also a gain in terms of perspective. From the vantage point of the present, looking back at this forgotten world helps highlight how contingent Earth's history is. The world we know is not the inevitable outcome of a simple, linear process. It is the result of a long series of arrangements and rearrangements, each one opening some paths and closing others. Pannotia represents one of those key arrangements, brief but influential, subtle in its traces but wide-reaching in its effects. By understanding what the planet gained from it, we get a clearer picture of how deep time works, how slow processes can have lasting impacts, and how the surface we walk on and the air we breathe are shaped by events that happened hundreds of millions of years ago. Step by step, over distances measured in thousands of kilometers and spans of time counted in hundreds of millions of years, the world continued its slow movement away from the brief moment when much of its land had gathered together as Penosia. Nothing snapped or jumped forward. Nothing marked a clean dividing line between the ancient world we've been exploring and the one that feels more familiar. Instead, the planet carried on, adjusting its shape, its climate, and its living systems in small, steady increments that, taken together, reshaped everything. To follow that drift forward, it helps to imagine the continents not as fixed outlines on a map, but as travellers on a deep, slow river of moving rock. Each piece of land, once part of a larger whole, began its own journey across the surface of the Earth, guided by currents in the mantle below. Some of these journeys led toward future collisions. Others led into long periods of separation, with oceans widening between neighbours that had once shared coastlines. As these land masses moved, the planet's geography grew more complex. Instead of one dominant supercontinent, the world became a mosaic of continents, island chains, and shallow seas. Coastlines multiplied, new ocean basins deepened. The arrangement of land and water began to resemble, in a very broad sense, the pattern we recognize today, even though the specific shapes and positions were still very different. This growing complexity had a powerful influence on climate. With continents spread across different latitudes, the planet developed a wider range of temperature zones. Some regions drifted closer to the equator, receiving more direct sunlight and experiencing warmer conditions. Others moved toward the poles, where cooler climates and at times ice could take hold. The oceans, now less constrained by a single landmass, were able to circulate more freely around the globe. Currents carried warm water toward higher latitudes and returned cold water toward the equator. This movement of heat helped moderate extreme temperatures and created more stable conditions in many coastal regions. Stability in this sense does not mean that the climate stopped changing. It means that the swings became less likely to reach the kind of global extremes seen during the snowball Earth periods. Instead of the whole planet freezing or warming at once, changes tended to be more regional, affecting some areas more strongly than others. This kind of climate pattern is one of the foundations of the modern world. It allows for deserts, forests, ice caps, and tropical seas to exist at the same time, each shaped by its position relative to the sun, the oceans, and the flow of air. As the continents continued their drift, the atmosphere also evolved. Oxygen levels, which had been rising through the late Neoproterozoic and into the Cambrian, continued to increase over long periods. This had several important effects. A thicker ozone layer formed in the upper atmosphere, providing greater protection from ultraviolet radiation. This made it safer for life to exist closer to the surface of the water and, eventually, on land. The presence of more oxygen also allowed organisms to develop higher energy metabolisms. This supported larger body sizes, more active movement, and more complex internal structures. In the oceans, these changes were already visible during the Cambrian, as animals with shells, exoskeletons, and jointed limbs became more common. Over time, this trend continued, leading to increasingly complex marine ecosystems. Reefs formed, built by organisms that could create rigid, mineralized structures. These reefs provided shelter, feeding grounds, and new niches for a wide variety of creatures. The seafloor, once dominated by flat microbial mats and soft sediments, became a three-dimensional environment, shaped by burrows, shells, and the physical presence of animals. On land, the transformation was slower, but just as significant. For a long time after Penosia, the continents remained largely barren, at least in terms of visible, complex life. Microorganisms may have lived on rock surfaces and in thin films of moisture, but there were no forests, no grasses, no animals walking across the surface. Eventually, however, plants began to make the transition from water to land. The first land plants were small and simple, lacking roots, leaves, or strong support structures. They lived close to the ground in damp environments where water was readily available. Even so, their arrival marked a turning point. Plants changed the way the land interacted with the atmosphere and the climate. Through photosynthesis, they drew carbon dioxide out of the air and released oxygen. Their bodies, when they died and were buried, helped lock carbon away in sediments. Their roots, even in early forms, began to break down rock, accelerating weathering and the formation of soil. This process increased the flow of nutrients from the land into rivers and oceans, which in turn influenced marine ecosystems. So the spread of life onto land created a new set of feedback loops, linking the continents more tightly to the chemistry of the oceans and the composition of the atmosphere. Animals followed plants onto land much later, and their arrival added another layer of interaction. Herbivores fed on plants, predators fed on herbivores. Burrowing animals mixed the soil, changing how water and air moved through it. Larger animals influenced the structure of vegetation by grazing and trampling. All of this contributed to the development of landscapes that are shaped not just by wind, water and ice, but by living things. From this perspective, the world we know today, with its forests, grasslands, reefs and diverse animal life, is the result of a long chain of changes that can be traced back, in part, to the rearrangement of the planet during and after Penosia's time. The continents that drifted away from that early supercontinent did not just move across the surface. They carried with them the conditions and the opportunities that allowed life to expand in new directions. There is also a geological story unfolding alongside this biological one. As continents continued to move, they collided again in new configurations, forming later supercontinents such as Gondwana, and much later Pangaea. Each of these gatherings and separations reshaped the planet's surface in different ways, creating new mountain ranges, new ocean basins, and new patterns of climate. The rocks beneath your feet today, no matter where you are in the world, likely carry the imprint of these ancient movements. Some may have been formed in deep oceans and later lifted into mountains. Others may have been part of long-eroded highlands that once stood tall during the time of Penosia or its successors. So even in the most ordinary stone there can be a connection to this deep past. Another part of drifting forward is the way the planet's magnetic field and rotation have influenced its surface over time. The magnetic field generated by the movement of molten metal in the core protects the atmosphere from being stripped away by the solar wind. This protection has helped preserve the air and water that life depends on. The rotation of the Earth and the tilt of its axis influence the pattern of seasons and the distribution of sunlight across the globe. These factors were present during Penosia's time, but their effects became more pronounced as the planet's surface grew more complex and as life began to occupy a wider range of environments. Seasonal cycles, for example, play a major role in shaping modern ecosystems. They influence when plants grow, when animals migrate, and how energy flows through food webs. While the specifics of these cycles have changed over time, the basic framework has been in place for hundreds of millions of years, providing another layer of continuity between the ancient world and the present. There is also a sense in which the planet has become more interconnected as it has evolved. In the deep past, when life was confined to the oceans and largely microbial, changes in one part of the world might have had limited effects elsewhere. As life became more complex and spread across land and sea, the influence of biological processes on the atmosphere and climate increased. Today, the actions of living organisms, including humans, can affect the composition of the air, the flow of rivers, and the chemistry of the oceans on a global scale. This level of connection has its roots in the long history of feedback loops that began to take shape during the time of Penosia and grew more elaborate over the periods that followed. From a broader viewpoint, drifting forward from Penosia to the living planet we know is not just a story of change, but a story of accumulation. Each phase of the planet's history adds something to what came before. The early microbial world established the basic chemical cycles. The rise of complex life added new layers of interaction. The spread of life onto land transformed the surface and the atmosphere. The movement of continents created a shifting stage on which all of this played out, altering the rules of climate and geography over and over again. None of these elements operates in isolation. They form a system, one that has become increasingly intricate over time. This system is also marked by moments of disruption. Mass extinctions, rapid climate shifts, and major geological events have periodically reset parts of the living world. Each time, life has responded by diversifying again, often in new and unexpected ways. These disruptions are not separate from the long-term processes we've been following. They are part of the same dynamic planet, one where stability and change exist side by side. Looking at the world today, it's easy to see the immediate surface-level features: mountains, oceans, forests, cities, clouds. It's harder to see the deeper connections that tie these features to events hundreds of millions of years in the past. But they are there. The shape of a coastline can reflect the outline of a rift that opened when Penosia was breaking apart. The minerals in a shell can trace their origin to chemical cycles influenced by ancient glaciations and volcanic activity. The oxygen in the air carries the signature of countless generations of photosynthetic organisms that began their work in shallow seas long before animals walked on land. So drifting forward is not just about moving away from the past. It's about carrying the past along, embedded in the present. There is also a human dimension to this story, even though humans appear very late in the timeline. Our ability to study rocks, fossils, and the chemistry of the Earth allows us to reconstruct worlds that no one ever saw. It lets us build a narrative that connects our moment in time to events that happened hundreds of millions of years ago. In doing so, it changes how we see our place on the planet. The world is not a static backdrop for human history. It is a dynamic, evolving system with its own long story, one in which our chapter is relatively brief. Understanding that story, even in a quiet, reflective way, can shift our perspective. The continents beneath us have travelled. The air around us has changed composition. The life we see is the result of countless experiments and adjustments. All of this suggests a kind of continuity that extends far beyond any single species or era. As the narrative settles into this broader view, it naturally circles back to the idea of movement. The planet is still drifting. The continents are still moving, even now at the pace of growing fingernails. New ocean crust is still forming along mid-ocean ridges. Old crust is still being pulled back into the mantle at subduction zones. Mountains are still rising in some places and eroding in others. Rivers are still carrying sediments to the sea. The atmosphere is still exchanging gases with the oceans and the living world. The systems that shaped Penosia and guided the planet through its breakup are still at work. What has changed is the level of complexity built on top of those systems. The living planet we know today includes forests that influence rainfall, coral reefs that shape coastlines, and human societies that alter landscapes on a scale comparable to some geological processes. This adds a new layer to the story, one where life is not just shaped by the planet, but actively shaping it in return. From this point of view, drifting forward is an ongoing process, not something that ended with the formation of modern continents or the rise of familiar ecosystems. The future will bring new arrangements of land and sea, new climates, and new forms of life. The story that began with ancient supercontinents like Penosia is still being written, and as you hold that thought, the sense of deep time and slow movement can linger, connecting the quiet, distant past we've explored with the living, changing world that surrounds you now. A world that continues to move forward, shaped by the same patient forces that once gathered and scattered a forgotten supercontinent across the surface of an ever-restless planet.